Hello, hi, namaskar everyone. Give me a quick response, quick update. Am I clearly visible? Am I clearly audible? Can you all see the screen right there in front of you? Can you all see me? I hope it is running smoothly. You all can hear me, you all can see me. The stream is running smoothly and you all are clearly able to see us and listen to us. And with this confirmation, shall we get started everyone? Here we are with our series that when we are preparing you to consolidate all the basics, all the learnings from that NCRT level. So gradually we build that whole theory, that comprehensive knowledge, awareness of all the formulae, all the concepts, everything we bring here. And gradually, once we are done with that, we gradually level up you with the good level of questions. And of course, we take you to JEE mains and advanced level. I welcome you all to this series. And of course, we all know, we all believe that one shots are never sufficient for JEE mains and advanced. But what they are sufficient for is that you can always consolidate a quick summary, a quick revision, a quick go through of a particular chapter. So in case if you have missed matrices, here you have an opportunity to watch this video and cover it totally, absolutely, completely. Or let's say you want to avail this opportunity where watching this one video can cover your entire theory of this chapter matrices. Possibly here is a video through which you can. But sir, will it be sufficient for us to cover up till JEE mains and advanced level? Theoretically, yes. But conceptually, in terms of practice wise, if I talk about in that sense, you need more practice. So if I were to suggest you something really important and crucial, what you need to do after watching this session, it will be one single advice that once you're done with this session, you need to do this simple task. You need to perform this simple task that solve PYQs. Once you are done with this theory of this chapter, solve PYQs. Initially, begin with the mains. So from matrices, solve the last 5 to 6 years PYQs from 2000 to 2026. And then once you're done with the PYQs of mains, go through the PYQs of JEE Advanced. And even in JEE Advanced, when you are solving the PYQs, begin with the 2000. Of course, here last 5 to 6 years. So 2020 to 2026 is fine. But in JEE Advanced, I'll say from 2000 to 2026, all the PYQs. And trust me, you have my affirmation, you have my confirmation, you have my assurance that nothing will go beyond it. Definitely, Shweta. In this session, I'll try to cover that. Don't worry. Probably in the end, when we talk about matrix, polynomial, characteristic equation, Cayley-Hamilton method and all, there I'll be bringing that. So don't worry. Even with binomial expansion also we do it, and that also will cover it here. Definitely you can, but determinant is something really basic. If you know the expansion of determinants, it will be fine. You will be able to understand and digest the chapter. Trust me. If you know the basic expansion of a determinant and if a shortcut you know the Sarah's technique of expansion of determinant, then it will be icing on the cake. Right, students? So shall we get started? The basic prerequisite I'm having. With this, I hope you know the feature of pylons we have launched. This is not just another feature we have launched. This is one of those features with the help of which you can not only participate in the polls we'll be conducting today, but also, let's say you want a quick summary, you want PYQs, you want mind maps, you want anything related to any random video you're watching on YouTube, you can generate a lot of stuff, a lot of related resource based on that video at absolutely free of cost. With this one application, Pylons, which you can install from Google Play Store or Chrome Store. So, of course it is, but as I have already mentioned that you need to solve previous year's questions. That's what you cannot skip. That's what you are mandatorily supposed to do. So shall we get started? If I talk about the topics which we'll be covering is, the simplest idea is I'll try to brief you on matrices. Then we'll talk about different type of operations you can perform, the algebra of matrices. And once we are done with this, algebra means addition, subtraction, equality of matrices, multiplication of matrices, and so on. And then our major discussion will revolve around the types of matrices. Trust me, based on this, a lot of questions are asked by JEE mains and advanced. And gradually we'll move towards the higher part where you talk about, different properties related to adjoint, related to inverse, related to different methods of solving equations. And along with this, do remember the most important part, matrix polynomial, which is also known as Cayley-Hamilton method, or even the characteristic equations or characteristic roots. But before we get started with all what we are supposed to study, first of all, what is a matrix? Matrix, first of all, is simply an arrangement. As we have been constantly mentioning throughout our sessions or lectures, if let's say you look at your Google sheet, an Excel sheet, there you have rows and columns, and the data is systematically arranged in it. So that whole sheet is a collection of data where numbers or values are kept or arranged in rows and columns. Similarly, that sheet does not have a value. It's merely an arrangement for you, arrangement of data in rows and columns. So matrix as a whole is simply an arrangement of data or values or elements of or entries in rows and columns. So, sir, when you talk about rows and columns, what do you exactly mean by that? I am trying to tell you that, let's say, if I define a 2 by 3 matrix, duration, it may last till 2 o'clock or 3 o'clock in the morning tonight. We'll try to cover it as soon as possible, but I don't know. So I'll just try to keep it slow, keep it understandable, ensuring that yes, you do all get everything, whatever is being explained. I'll not rush unnecessarily, but of course, we'll try to cover everything. That's assurance I'm giving to you here through this video. So when I wish to say 2 by 3, it means this is the number of rows and this 3 represents the number of columns, which means what? If it has 2 rows, it will have 3 columns. Can somebody tell me with the basic maths in their brain, 2 into 3, number of elements, this matrix is going to be how many? I hope you are clearly realizing. So if 2 rows and 3 columns are there, clearly it is going to have 6 elements. So 6 elements could look like this: 2, minus 1, 0. I hope you're realizing first row, 3 columns. Second row, 3, 5, and 7. So second row, again 3 columns. So 2 rows and 3 columns. That's how you see arrangement of data in a matrix. I hope very basic, very clear, very much understandable. Now, if I talk about the data, the placement of the data, how do we talk about the corresponding terms or positioning of these terms? First of all, look at this. This element 2 is first row and first column element. So I could denote it as A11. This element minus 1 is first row, second column element. The 0 is an element which is positioned in first row but third column. So it is going to be A13. Now if I talk about this 3, it is second row, first column. This 5 is positioned in second row, second column. And this 7 is positioned at second row but third column. So this is how positioning of these elements is defined. I hope so far there is no confusion. You're able to process the positioning part comfortably, yes or no, all the participants. With this, I hope whatever is mentioned here, this PDF will be given to you, provided to you for your revision. You can avail this PDF by following our WhatsApp channel. Our WhatsApp channel you can follow by just seeing the link in the description. And once the session gets over, this entire PDF will be given to you, will be provided to you. So usually a matrix is denoted by this parenthesis, Aij m cross n. Aij m cross n clearly means these elements which we have just seen over here, Aij, which means A11, A12, A13, A21, A22, A23. And what is m cross n? This is rows and columns. So 2 into 3, that's your m cross n. I hope something very basic, easy and understandable. No confusion regarding this. This whole part is very well understood by you all. Now, whatever we have understood so far, let's quickly get a decent clarity on that with this example over here, shall we? The question here says that a matrix has 28 elements. There is a matrix given to us which has 28 elements. Now, what are they asking? What are the possible orders? What are the possible orders it can have? Possible order means what? Something really basic, easy and doable. If I ask you this question, will you not say, sir, it can have one row? And if it can have one row, that means 28 columns it has to have. Because I need to ensure that it has 28 elements. So if I wish to ensure that it has 20 elements, with one row and 28 columns, I can ensure 28 elements. And when you plot it, when you arrange it, it will look somewhat like this. First row, first element, first row, second element, and so on until first row, 28th element. And that's how you write all these elements in just one row. And this matrix is said to be a row matrix. What do you mean by row matrix, sir? Row matrix means that if there is a matrix which has only one row, Sir, what about number of columns? They can be many. They can be as many as needed or required as per the data. But if it has only one row, it will be said to be a row matrix. Based on it, opposite of it will also exist. I mean, swapping of it, which means if 1 into 28 can be a possibly acceptable pair, then 28 into 1 can also be a possibly acceptable pair. What is 28 into 1? So this time I have 28 rows, but exactly in only one column. So how will you represent it? I hope you're realizing if you have 28 rows like this, but only one column. So this is a 28 by 1 matrix, where this is the first row, first column. Now this is second row, first column. This is third row, first column, and so on. And that's how I'll be writing all the 28 elements. Getting it or not, everyone? So sir, other possible combination could be 28 into 1. Yes or no, all the participants? With this, sir, what all other possible combinations it can have? I think let's go ahead with this. 1 into 28, can I have 2 into 14? Yes. So 2 rows, 14 columns. So if 2 rows and 14 columns are there, sir, 14 rows and 2 columns could also be there. Sir, 28 divisible by 3? No. 28 divisible by 4? Yes. So I can write it as 4 into 7. So if 4 is 4 rows and 7 columns, it can have 7 rows and 4 columns too. Yes or no? 28 is clearly not divisible by 5, 6. And ultimately, when I go to 7, I think 7 I have already considered. Then I'll have 14, which I have already considered. Then I'll have 21, which also I have already considered. So I think nothing is left untouched. If you are still confused, what you can do is, for your verification, 28, if you prime factorize, it is 4 into 7. So 4 is what? 2 square. 7 is what? 7 to the power 1. And I think with this, whatever possible combinations we could create, we have already created. So there will be 6 possible combinations. Tell me in the comments, have you also gotten these possible orders only? Or did you have some other combinations as well? Everybody understood this whole idea? Are we clear on this? Yes or no? Shall I move ahead from here? With this creation of matrices, let's say data regarding matrix is given, and then we need to create a matrix. So this question I'm giving you as a homework. The second part I am doing here. Here, the element Aij for a 2 by 2 matrix is given by mod of minus 2i plus 3j. Now, how do I create these elements? I'll simply say that, sir, if you are able to create a 2 by 2 matrix, I want to create a 2 by 2 matrix. Yes. So I hope position wise, if I could relate or locate those elements, I'll say this will be first row, first column, first row, second column, second row, first column, and second row, second column. So this is your I and this is your J. Everyone comfortably able to process all of this, whatever is said so far? Yes or no? With this, will you all not say that, sir, if you want to define these elements, how will you say? Or how will you define? Sir, if this matrix is needed to be created, this has its elements definition given by mod of minus 2i plus 3j, which means 2 into 1, minus 2 into 1, plus 3 into 1. So this will be minus 2 plus 3 inside the mod. That's your first element. Second element, if I wish to define 1, 2. So how will I define 1, 2? Sir, 1 and 2. So minus 2 plus 6. I hope you're getting it. So it will be mod over minus 2 plus 6. Everybody getting that? If I wish to proceed ahead further, I'll say a to 1. How will I define a to 1? 2 and 1. So that's minus 4 plus 3. So it will be inside mod minus 4 plus 3. And then the final element, which is given by a to 2. What is a to 2? So 2 here, 2 here. So that is minus 4 plus 6. I hope you're getting it. So mod over minus 4 plus 6. I hope it's readable when I overwrite over this child's face. Right. So with this, when I finally wish to write the matrix for the second question, I'm solving it here. Do write your answer in the comment box as well if you can crack this question. So it is given by 3 minus 2, 1, 6 minus 2, 4. There you have minus 4 plus 3 minus 1, but mod over minus 1 is 1. And that 6 minus 4 is 2. And its magnitude is also going to be 2. How many of you got it? How many of you cracked it? How many of you were able to think like this? Tell me in the comments. Everybody able to process this? Everybody understood this? So I hope there is no confusion regarding formation of a matrix. So if position of an element is given by these A11, A12, and so on, and if a matrix element's position is given by -2i plus 3j inside a mod, then how do we take those elements? How do we define those elements? Did you get a crystal clear idea on that? Yes or no, everybody? Be quick. Everybody comfortably getting it? Any confusion so far? Great, brilliant. With this, let's move ahead. Let us now understand different types of matrices. For example, if I talk about row matrix, have we not already discussed it? I hope you do remember when we talk about row matrix. What is the meaning of row matrix? If there is a matrix which has only one row, if it has only one row, for example, look at this. This matrix is of what order? Sir, if you locate its order, it is going to be one row but four columns. So 1 by 4. So 1 into 2, 1 into 4, 1 into 5, 1 into 6, if something like that goes on, I'll say that this is clearly a row matrix because it has a fixed one row. Yes or no, everyone? The session will last till 12 o'clock or 1 o'clock possibly because we'll cover it comprehensively, thoroughly, the whole chapter. Right? Now with this, if I talk about the column matrix, I hope you have understood row matrix. Can you not make some sense out of column matrix now? So what do you mean by column matrix? If it is 1 by 1, it is both. It is row matrix as well as column matrix. It is a square matrix as well, Natraj. So with this, if I wish to define this matrix, it has only in exactly one column, but it has three rows. Rows are fine. So if it is three rows, one column, I'll say this is a column matrix. So n into 1, 5 into 1, 7 into 1, something like that if I'm given. 1 is the number of columns. And if it is 1 only, then I'll call it a column matrix. Everybody comfortably got this two-part, row matrix and column matrix. With this, if I talk about the null matrix, if any matrix is there which has all the elements defined as 0, if there is any matrix which has all the elements defined as 0, 0, 0, 0, 0. So this is a 2 by 2 matrix which has all the entries are 0. Then we say that it is a 2 by 2 matrix which is being more specific, either a null matrix or a 0 matrix. Everybody got this? Yes or no? All the participants. With this, when we talk about a square matrix, now that's where the actual chapter begins. Because matrices we usually convert into determinants. We perform an operation on matrices and then we take determinants of them. Of what kind of matrices, sir? When we deal with the matrices which are square matrices. Sir, what do you mean by square matrices? Square matrices means what? Square matrices here means that if you ever deal with a 1 by 1 matrix. So this matrix has a number of rows and columns to be 1. This is a square matrix, 1 row, 1 column. So if this is a matrix A, and if you are asked to find out its determinant, like addition, subtraction, determinant is also a mathematical tool, an operator which you perform on square matrices. So if there is a square matrix of order 1, 1 row, 1 column. So there if I take its determinant is given by determinant of A and determinant of A which is 2 here. Then I'll say technically it is determinant of this 1 by 1 matrix which is given by 2. So for a 1 by 1 matrix, the determinant of that matrix is the value of that element. Some of you may confuse it with modulus. This here does not represent the modulus sign. This sign here is not modulus. This sign here is not modulus sign. This sign here is the sign of determinant. For example, just to keep it understandable, let's say I give you a matrix X which has an entry minus 5.3. This is a matrix X which has what? 1 by 1 order because 1 row, 1 column. So if I ask you the determinant of X, so determinant of X means not the modulus of X. If it is 1 by 1, just that element which is given over there, minus 5.3. So its determinant is going to be minus 5.3 and that's the determinant of X. Always remember, if there is a matrix which is order 1 by 1, so the element which is given in that matrix will be the determinant of that matrix. Understandable, easy, simple, doable, yes or no? With this, if I could give you clarity on a 2 by 2, which we did discuss in the last session, if you remember, let's say that there is a matrix B, which is again a square matrix 2 by 2, which has elements 0, or let's say, which has elements 5, 4, 7, and 2. Now, sir, how do we define its determinant? Trust me, it is absolutely simple. Here, this is a 2 by 2 matrix. So its determinant is given by these two lines over this matrix. I repeat, it is not magnitude here or the absolute value here or the numerical value here. It is not modulus here. It means whenever you wish to define its determinant of a square matrix, which is a 2 by 2, then its matrix is found by determinant of these four entries 5, 4, 7, 2, and to expand it to find its numerical value. Matrices don't have any numerical value. It's merely an arrangement of rows and columns. But when you look for the value of a determinant, it is a numerical value. How do we find the numerical value? To find the numerical value, we multiply 5 with this 2 here, and we multiply this 7 with this 4 here. Then what do? 5 into 2 is 10 here, 4 into 7 is 28 here. So 5 into 2 minus 7 into 4, that's 10 minus 28, and that is clearly minus 18. So here, determinant of this matrix B, which is a 2 by 2, is given by minus 18. Yes or no? Everyone, pay attention on the next part here. If I'm given a matrix C, which is a 3 by 3 matrix, for which the expansion is really simple. The expansion is absolutely simple. The expansion we have already learned in the last session, determinants. Do you remember that? In determinants, we did discuss how do you expand a 3 by 3 matrix. Not just that standard expansion method, but also we gave you that Sarus rule as well. Do you remember that whole idea? Yes or no, everyone? So if I could simply and quickly give you that expansion, which we have already discussed in the last session, I'll be giving you here. Pay attention, everyone. Let's say it has entries like 2, 3, 1. Then let's say minus 1, 7, 4. Then let's say 2, 4, and let's say 9. So if I wish to expand it, for a 3 by 3 matrix, you can always expand it with respect to any row or any column. Let's say I wish to expand it with respect to the first row. So how will you expand it with respect to some row or a certain row? Let's say 2, 3, 1. So I'll write this 2. I'll write this 3. I'll write this 1. Now I'll write their cofactors. If you are confused with what cofactors are, go back and watch the video on determinants, which we have dedicatedly recorded. In this series, the previous lecture was determinants only. And there we have covered this whole process. Although in matrices, we would need it. That's why I'm covering it again, but you really don't need it if you have sincerely watched the previous session determinants. So for a 3 by 3, I take any row or any column, I write its elements, and then I write its cofactors. So what do you mean by cofactors? For writing the cofactor of 2, what I'll do is I'll remove this row in column, which contains 2. I am left with these 4 elements, and I'll just write their determinant. So here I'll be writing it as determinant of 7449. I'll write it as 7449. But sir, you said cofactor. I think it's minor. Cofactor means sign scheme also you follow. Sir, what do you mean by sign scheme? Sign scheme means this 2 has this position A11. Add this 1 and 1. So this 1 plus 1 is 2. What is 2? Even or odd? 2 is even. So put a positive sign over 2 before 2. And I think 2 is already positive. There is already a positive sign. Positive sign you don't have to mention explicitly before the first term. So I'm not putting any sign. But for this 3, if I wish to define its cofactor, let me define its minor first. For this 3, if I remove this row and this column, I'll be left with these 4 elements. I hope you're clearly noticing. So these 4 elements determinant I'll take, and then I'll introduce the sign scheme as well. But let me take the determinant here. The determinant goes like minus 1, then you have this 4, then you have this 2, and then you have this 9. But sir, this looks like minor only. What do you mean by cofactor? So for cofactor, I'll say this 3 is positioned at, this 3 is positioned at first row and second column. So its position is 1, 2. 1 plus 2 is 3. 3 is odd. Odd means you put a negative sign. So with this negative, this determinant now becomes cofactor of this 3. Getting it, everyone? So if you take any row or any column, and if you multiply those elements with their corresponding cofactors, you will see its determinant. Definitely. Now with this, let's talk about that one. For this one, if I wish to write the determinant, I hope everybody is clearly noticing that this row in this column you got to remove, and that's where you're left with these four elements. So you write these four elements here. These four elements are going to be -1, 7, 2, and 4. But sir, what about the sign? Locate its position. It's positioned at first row, third column. First row, third column. So 1 plus 3 is 4. 4 is even. That means a plus sign. So if even plus sign, if odd minus sign. Getting it, everyone? With this, I think we have the value of this 3 by 3 matrix determinant. So if I am interested in finding, the determinant of C, I think our job is done. Why? Let's talk about that part now. I hope everyone is paying complete attention here. So this determinant of C here is given by 2 times. 7 into 9, that is 63, minus 4 into 4, that is 16, minus 3 times minus 1 into 9, that's minus 9, 4 into 2, that's minus 8. Getting it, everyone? With this plus 1 times minus 1 into 4, that's minus 4, and 2 into 7, that's 14. And if you add it up, you will get your final answer. Yes or no? Everybody simply understood this, got a complete idea, got the whole picture now. Are you all comfortable with how you expand a determinant? Yes or no, everybody? With this, I think we can go ahead with a simple idea that if I am ever seeing a matrix, which is of course a square matrix, and if I wish to see that what are its leading diagonal or principal diagonal and what are its term, what is the upper triangle, what is the lower triangle, let's talk about all of those terms one after another, shall we? So if I could begin with the first thing here, what is that first thing? Look at these terms, 1, 3, and 5. Are you noticing it? If you locate these three terms, 1, 3, 5, you will notice that, sir, this 1 is A11, this 3 is A22, and this 5 is A33. So these three elements, A11, A22, and A33, they all are your principal diagonal elements. Or some books call them the principal diagonal elements as well, or leading diagonal elements. First of all, did you get that? All the participants, be quick, be clear, and be crystal clear on this. Have you all gotten this? Have you all understood this? Now with this, one more thing I want to clarify here is something really important. Pay attention. This is your leading diagonal. This here is your leading diagonal. I hope you're noticing it. So here, all I'm saying is that look at these three elements. 1, 3, 5, which we have taken as principal diagonal elements. If apart from this 1, 3, 5, if you look at this 2, 0, 6, I hope you're noticing it, 2, 0, 6. So that's your upper triangular. And these three elements which you notice here, minus 5, minus 1, and 4, that's your lower triangle. Sir, why are we discussing all this? Okay, I want to highlight something really beautiful and interesting here. If you just pay attention to that part which I'm mentioning here. Look at something really beautiful and interesting. A11, A22, and A33 you already know. Yes or no? Everybody knows that. Now, if I talk about these upper triangular elements, look at that. A12, A13, and this is A23. Look at these upper triangular elements. In these upper triangular elements, if you notice, you would be noticing something really interesting. Let me just flip it so that you will realize something really beautiful here. Yes, these three elements. Look at these three elements. Are you all noticing that, sir, 1, 1, 2, 2, 3, 3. So 1, 2, 2 is greater, 1, 3, 3 is greater, 2, 3, 3 is greater. So for these elements, if you are positioning them as Aij, you will notice that, sir, in these elements, J is always greater than I, or I is always less than J. Yes or no? Sir, what about principal diagonal elements? I hope everybody is very clearly noticing that, sir, if you are talking about the principal diagonal elements, it is clearly understandable that in principal diagonal elements, A11, A22, A33. So what do you mean by that? I just want to say a simple idea that for the principal diagonal elements, you will be noticing I and J to be same. Yes or no, everybody? Sir, what about this part, the lower triangle? I think you have the definition now, yes or no? You can notice it by yourself. This element is positioned as A21, this is A31, and this is A32. Now look at this, 2 is greater than 1, 3 is greater than 1, 3 is greater than 2. So for these lower triangular elements, I hope everybody is very clearly noticing that if you are defining them as Aij, there you are clearly noticing I is greater than J. Everybody got this basic idea? How do you define lower triangle, principal diagonal and upper triangle? Sorry, upper triangle, principal diagonal and lower triangle. Everybody understanding this mathematical definition as well? Yes or no? With this, if I go ahead with this basic idea, let us now talk about the diagonal matrix. What do we mean by a diagonal matrix? So basically now whatever classification we are going to do, that whole classification will lie or revolve around a square matrix. So what is a square matrix? If number of rows and columns are same, 1 by 1, 2 by 2, 3 by 3, 4 by 4 and so on. But your syllabus is majorly restricted to 1 by 1, 2 by 2 or 3 by 3 matrices. Yes, mostly, or rather almost always. Now, whenever we talk about a diagonal matrix, so first of all, it has to be a square matrix. And if all the elements in upper triangular and in lower triangle are 0, or let's say all the non-diagonal elements are 0. I hope you are clearly noticing it to be here like this, that here, these principal diagonal elements, whatever they are, I don't care. They can be 0, they can be non-zero. We don't mind them. But apart from that, I hope you are clearly noticing these non-diagonal elements, if they all are 0, then we say that such matrix is said to be a diagonal matrix. Everybody understood that? Or shall I re-explain that part? And in the world of matrices, a diagonal matrix is given by dic d1, d2, d3, dn. What does it mean? Let's say if I wish to write this matrix. So this matrix, which is matrix A, which is luckily a diagonal matrix because it's non-diagonal matrix, all are 0. There I can write it as diagonal 3, 5, minus 1, which means its diagonal elements are 3, 5, and minus 1, and all the other elements are 0. One more very crucial property you should remember, that whenever you see a diagonal matrix, its determinant is always given by product of its leading diagonal elements, which means its determinant is going to be 3 into 5 into minus 1, which is clearly minus 15. You really don't have to use expansion or any other method or shortcut like Sarah's rule. You can directly say that its expansion will be written as product of its principal diagonal elements. Is it very well understood by everyone? Have you all been able to process it? Yes or no, all the participants? Tell me honestly. So far, is there any confusion? Shall I move ahead from here? Now, sir, if you have understood the diagonal matrix, can you explain scalar matrix? Yes. What is a scalar matrix? So if I introduce the concept of scalar matrix, first of all, now we are narrowing it down. So first of all, we had a square matrix. Then after a square matrix, we moved towards what? A diagonal matrix. Now in a diagonal matrix, sir, what is a diagonal matrix? All the non-diagonal elements are supposed to be 0. So if in a diagonal matrix, if its diagonal elements are same, if all of its diagonal elements are a fixed value, then always remember such matrix is said to be a scalar matrix. Then how does it look like? You yourself define this definition. Let's say there is a matrix A, which is, let's say, a 3 by 3 matrix, Sir, whenever I and J are equal, A11, A22, A33, So whenever I and j are equal, it has to have a same value. Let's say that same value here in this case is -7. So A11, A22 and A33 are a fixed value. But apart from that, all the other values, when I and j are not equal, like A12, A13, A21, A23, A31, A32, for these values, when I and j are not equal, it has to contain 0, because ultimately in the end, what was it? It was a diagonal matrix. But if in a diagonal matrix, all the elements are static, fixed, same, then instead of calling it diagonal only, I'll call it specifically a scalar matrix. So there, all these entries will be what? 0. Comfortably getting it, all the participants. I hope scalar matrix is very well understood by everyone. Shall I move ahead from here? Yes or no? Now there comes the most important matrices, which is called a unit matrix or an identity matrix. We see in the world of numbers, 1 is there. Now how does 1 behave? I hope you remember, 1 behaves as what? 1 behaves as 1 into 3, 1 into 3 is 3, 1 into 5 is what? 5, 1 into -7 is -7. So in that same fashion, identity matrix or unit matrix exist in the world of these numbers or in the world of matrices. What do you mean by that? Let's talk about that here. Unit matrix or identity matrix is clearly a scalar matrix, first of all. But a specific kind of a scalar matrix where that scalar entity, those principal diagonal elements become 1. So a square matrix narrowed down as diagonal matrix. It narrowed down as a scalar matrix. Now that scalar matrix, a very specific case, is turning out to be as an identity matrix. So what do you mean by identity matrix? In identity matrix, you will see for the principal diagonal elements, for example, A11, A22, A33, it has to be 1. For all the non-principal diagonal elements, for A12, A13, A21, A23, A31, A32, it is going to be 0. So how does it look like? It is clearly visible. A11, A22, A33 is 1, 1, 1 each. But all the other non-principal diagonal elements are clearly 0. Everybody able to make some sense out of it? That what do we mean by an identity matrix? Yes or no? All the participants. Everyone understood this comfortably. The concept of unit matrix, the concept of an identity matrix. So 4 things we have discussed. First of all, a square matrix. Then we moved towards diagonal. Then we moved towards scalar. And then we are discussing unit. Subsets. I hope if I could define it like this, we had matrices. A specific case of matrices of what? Square matrices. Yes or no? And in square matrices, when we created a specific case, it was what? A diagonal matrix. You remember that? From a diagonal matrix, more specific case which we created was of scalar matrices. And in scalar matrices also, a more specific case which got created was of the identity matrix. So far, majorly this discussion we have done, and I'm sure you have been able to process all of these matrices comfortably. Yes or no? All the participants. With this, now let's talk about how does a triangular matrix look like. So let me give you an example here. When I talk about the, let's say, upper triangular. So what do we mean by an upper triangular matrix? If all the elements below the principal diagonal are 0. I hope you remember, a square matrix is called upper triangular if all the elements below the principal diagonal are 0. Which means what? Let me just create a case. Let's say there is a matrix A which has a order 3 by 3 and order 3 by 3. For this matrix 3 by 3, if there is a diagonal, principal diagonal could be anything, let's say 7, 3, 2. Now, what is it saying? All the elements below the principal diagonal are 0. So below this principal diagonal, if all the elements are 0. So what about the upper elements? They could be anything. So they could be -1, 7, 5, anything. So I hope you all are clearly noticing that, sir, in this matrix, I am seeing that an upper triangle is getting created with these elements. If I keep all these zeros which are below the principal diagonal, if I keep them aside, I am seeing an upper triangle getting created. So this matrix over here is said to be an upper triangular matrix. In that same fashion, can you not define the lower triangular matrix? Let's try and define a lower triangular matrix for a matrix B. How do we give it? How do we define it? Let's say this is a 2 by 2. For lower, I hope you're realizing, below the diagonal, all the elements, I don't care, but above the diagonal, all the elements are supposed to be 0. For example, here, the principal diagonal is 1, 2. So above the principal diagonal, all of these elements should be 0. This can be anything. And here, I'm sure you must be very clearly noticing that this is forming a lower triangular. So this here is stated as a lower triangular matrix. So why are we calling it a lower triangular matrix? Because this is your diagonal, principal diagonal, leading diagonal, and above it, everything is 0. So with this leading diagonal and all the other elements, I'm able to create or form a triangle, which is a lower triangular matrix. This was an upper triangular matrix. Mathematically, how do we define it? I hope you are clearly noticing that here, this is A21, A31, A32. So for all these elements, what was there? I hope you are clearly noticing that this was A21, A31, A32. So I was clearly greater than J. So if I was clearly greater than J, we defined Aij as 0. If Aij is 0, for all I which are greater than J, they are said to be forming the upper triangular matrix. In the same manner, let's say if I'm defining the lower triangular matrix, look at this element. This element is positioned at A12, first row, second column. So A12 means what? Here, if I define it as Aij will be 0, but for what kind of elements? Sir, A12, which means I is less than J, which means all the J are greater than I. For all the J which are greater than I, if Aij is 0, such matrix formed with this property being fulfilled will be creating what kind of matrix? A lower triangular matrix. Give me a quick confirmation. Are you able to process an upper triangular and a lower triangular matrix? Yes or no, all the participants? I hope we are very comfortably moving ahead with this whole discussion. Symmetric matrix. We have done a detailed discussion on symmetric and skew-symmetric when we discussed the chapter Determinants. Do you remember that? But let's say I've forgotten that. So how do we bring it here? Again, pay attention everyone. There is a square matrix. And if Aij is equal to Aji for all ij, then we call such matrix to be a symmetric matrix. So what do you mean by that? Pay attention everyone. If I create a 3 by 3 matrix for you, position wise, so A11, is it equal to A11? Of course, sir, A11 and A11 are same. But when I talk about A12, so A12 should be equal to A21. A12 should be equal to A21. Similarly, if I talk about A13, so sir, A13 should be equal to A31. Aij should be equal to Aji. Now, I'll talk about A22. Sir, A22 is equal to A22. I hope my language is understandable, yes or no. With this, when I talk about A23, should be equal to A32. Aij should be equal to Aji. And the last element, which is A33. So, sir, do you notice A33 to be equal to A33? Yes, A33 is A33. Sir, we are not able to process this. Whatever you are saying is clearly not understandable. Okay, let me give you a little different idea here in this case. What is that? Let's talk about that. Hold on for a while, students. Here, these principal diagonal elements are A11, A22, A33. They don't matter. But this was your A12. This was A21. Are they same? Yes. This was your A13. This is your A31. Are they same? Yes. This is your A23. This is A32. Are they same? Yes. So this is a symmetric matrix. I repeat. Let's say I give you a totally different definition. A totally different definition. So what do you mean by that? Let's say there exists a matrix X. There exists a matrix X which is given by, let's say 2, 3, 5. And this is 3, 7. Let's say 4. This is 5, 4, 8. and let's say I take its transpose. Sir, what are you talking about? You are introducing another new term now. Transpose, what is that? Transpose means when you interchange rows in columns. When you interchange rows in columns means, let's say here the first row is 2, 3, 5. I'll call it first column. The second row is 3, 7, 4. I'll call it second column. The third row is 5, 4, 8. I'll call it the third column. So if I'm creating a matrix by interchanging rows into columns or column into rows or vice versa, if I luckily could get the same matrix, the original matrix, I hope you are noticing, sir, 2, 3, 5 was the first row. Here also 2, 3, 5 is the first row, even after taking the transpose. 3, 7, 4 was our second row. 3, 7, 4 is our second row, even after taking the transpose. 5, 4, 8 was our third row. 5, 4, 8 is our third row, even after taking the transpose, which means I noticed that X and its transpose are same. X and its transpose are same. So if a matrix and its transpose are same, you see this property getting fulfilled, that for a matrix Aij, Aji are equal. So either you say it like this, that a matrix and its transpose are equal, or if Aij is equals to Aji for all ij, then we say that such matrix is said to be a symmetric matrix. Everybody got this, or shall I re-explain this part? All the participants, be quick. Everybody got this, yes or no? Now, similarly, there exists one more kind of a matrix which is called a skew-symmetric matrix. Sir, what do you mean by skew-symmetric matrix? In symmetric matrix, what we noticed was, sir, Aij was equals to Aji. But if Aij is equals to minus Aji. Sir, what do you mean by that? Let me explain that with a very simple, straightforward example. Let's say here you have a 2 by 2 matrix, which has elements as A11, A12, A21, and A22. And this is a matrix, let's say X. So what I'm saying is that Aij should be equal to minus Aji for all the elements. It should be equal to minus Aji for all ij, which means A11 should be equal to minus A11. A12 should be equal to minus A21, which means A21 should be equal to minus A12, and A22 should be equal to minus A22. Now, can somebody help me with this idea? I am saying that a number is equal to negative of that number. When is it true? Sir, that happens only when that number is 0. A22 is equal to minus A22. When is it true? Sir, that happens only when that number is 0. Yes or no? So with this idea, will I not say that if I wish to define a skew-symmetric matrix, its principal diagonal elements A11 and A22 or A33, let's say for a 3 by 3, are going to be 0? So whenever you notice a skew-symmetric matrix, one thing which you all will notice is that, sir, its leading diagonal elements, its principal diagonal elements are all going to be 0. Everybody comfortably got this idea? Yes or no? With this. Second conclusion. I am saying that A21 and A12 should be equal in terms of magnitude, but opposite in sign. Which means if I am defining A21 as, let's say, 5, then A12 magnitude wise should be 5, but in terms of signature or sign, they should be opposite. Everybody got that? Same idea if I could give you for a 3 by 3 matrix. Here it is said to be a skew-symmetric matrix. One definition we have already seen, Aij is equals to minus Aji. If I could give you one more definition, will you not say that, sir, here you might say that if you take transpose of X, it should be minus X. If you take transpose of X, if I take transpose of this, if I take transpose of this, transpose means first row into first column, yes or no? Second row into second column, yes or no? And if I take negative common out of it, if you want to take a scalar quantity common out of a matrix, that comes out common as from all the elements. So if I'm taking negative common, negative of 0, negative of 5, negative of minus 5 and negative of 0. That's how you write it. Are you all not noticing 0 minus 5, 5, 0? 0 minus 5, 5, 0. Luckily, it is turning out to be minus x, and that's exactly my whole point. That when I took transpose of a matrix, and if I could get the negative of the original matrix, then we call such matrix to be clearly nothing but what? A skew-symmetric matrix. Everybody got that? Everybody understood that? The whole explanation? Any confusion so far? If you want to understand it with a 3 by 3, as I've already mentioned, if it is a skew-symmetric, first of all, its leading diagonal elements, its principal diagonal elements, all are going to be 0. Second thing, A12, A21, magnitude-wise same, but opposite in sign. A13, A31, magnitude-wise same, but opposite in sign. A23, A32, magnitude-wise same, but opposite in sign. Is my language understandable? Are you all able to process the concept of skew-symmetric matrix? And even if you take its transpose, it will be equal to negative of it. Getting it, everyone? Yes or no? So far, is there any confusion on whatever we have done? One more very crucial property I want to tell you here at this stage is that if you ever take the determinant of a matrix, where this matrix A is a skew-symmetric matrix of odd order. I hope you understand odd order. Odd means order 1, order 3, order 5, like that. So if you ever see a matrix which is both skew-symmetric as well as having odd order, without any hesitation, you can always say its determinant is going to be 0. Why? We'll understand it. But right now, I am asking you or requesting you to remember it as a property. Will you all? Yes or no? Any confusion so far regarding anything? Shall I move ahead from here? All what we have discussed. So let's quickly discuss a question and let's see how many of you get the answer. Shall we? The moment you get the answer, do write in the comments. I'll be really happy and glad if you could get the correct answer. Everyone, shall we start doing it? What is it saying? The maximum number of different elements required to form a symmetric matrix of order 12. How do we do it? Let me do it for a 3 by 3. And once I do it for a 3 by 3, I'll give you the logic and you can apply that logic for a 12 by 12. Will that be okay? So let's do it for a 3 by 3 matrix. Let's say this is not the question. I am solving a different question. What is that question? We are solving a question where the order is not 12, let's say for a while, the order is 3 for a while. Shall we take an order 3? So for an order 3, what is going to be the answer? Let's try and answer that. So if there is an 3, so 1, 2, 3, 4, 5, 6, 7, 8, 9, it is going to be a 3 by 3 matrix. Sir, what is the question here? The question is absolutely simple here, students. The question says that if I am asking you maximum number of different elements I can keep here. Let's say we are solving a 3 by 3 matrix and I'm asking you the maximum number of distinct elements I can keep here. First of all, sir, there is no problem with the principal diagonal elements. You can keep them whatever you want. So shall I say from here, these 3 elements, I can undoubtedly keep whatever I want them. So these 3 elements are going to be there, yes or no? Plus. Now, if I fix these 3, so these 3 are clearly dependent on that. So I hope you're now noticing that if I wish to keep it symmetric, the constraint here comes as this, that either upper triangle or lower triangle you can decide, and the other triangle will be dependent on the other triangle. If I could fix the upper triangle, lower triangle will be dependent on that. If I could fix the lower triangle, upper triangle will be based on that. So if it is a 3 by 3 element, how many elements are there in one of the triangles? Luckily here we are seeing it to be as 3, but is it really that just simple 3? No. Let me give you a little complicated approach here. Why? Just to establish the logic which we'll be needing here for a 12 by 12. Let us learn that. Can you help me the total number of elements it has? So the total number of elements it has are 3 into 3, that is 9. The total elements it has are 3 into 3, that's 9. From these 9 elements, if you remove the principal diagonal elements, so if it was a 3 by 3, if it was a 3 by 3 matrix, on the principal diagonal, it has 3 elements. On the principal diagonal, it has 3 elements. So from a 3 by 3, which has total 9 elements, if I remove the principal diagonal, how many elements am I left with? So you're left with non-principal diagonal elements, which are 6. If from the total elements, if you have removed the principal diagonal elements, you are left with non-principal diagonal elements. Yes or no? Which means what? I think if I half this number, which number? This. If I halve this number, I'll be left with either lower triangular elements or upper triangular matrix, and that's exactly what I needed, because those I can keep as whatever I want, because either I fix this or this, because if I fix this, it will be dependent on this. If I fix this, it will be dependent on that. So with this, I'll get it as 3 plus, that's 9 minus 3, which is 6 by 2, that is 3. Sir, it was such a simple question. Why did you really complicate it like this? What was the need of doing something like this? I think some of you may have noticed that when you're dealing with the 12 by 12 question, forget a 12 by 12 question if it is an n by n question. Let's say it is a matrix of order n. If it is a matrix of order n. So what liberty do we have? Sir, if you are talking in terms of liberty, principal diagonal elements, you can keep whatever you want. So this will be A11, A22, A33 and so on until what? ANN. So these are n elements which you can keep whatever you want. So I'll have first of all these elements kept as whatever I want. Apart from that, now if I talk about the total number of elements this matrix will have. So sir, the total number of this matrix, the total number of elements this matrix is going to have are going to be n square. Out of the total elements, if I subtract the principal diagonal elements, will I now not be left with either upper triangle or lower triangle elements? So what does this imply? N square minus n. N square minus n means all the upper triangle and all the lower triangle elements. Now to keep it symmetric, what constraint we have? So the constraint is absolutely simple. Either you choose, I hope you're understanding, these elements, or you choose these elements, yes or no. So these when fixed, these will be dependent on them, or these when fixed, these will be dependent on them. So I can choose either them or them. Others will be dependent on them. So total elements are n square minus n, upper triangular and lower triangular, where this principal diagonal is removed. Half of them I can decide, because I can decide either the upper triangle or lower triangle. So if half of them are there in my control, in my hands, so to decide, to ensure that it remains symmetric, that's a formula. That's a formula we have derived or developed for an n by n matrix. So here, if this is the formula for an n by n matrix, can you not tell me the answer to this question? Sir, it was a 12 by 12 matrix. It was a 12 by 12 matrix. So on its principal diagonal, how many elements will be there? Sir, the total number of elements on its principal diagonal will be 12. So total number of elements, will be 12 square. Out of which, if I remove the principal diagonal elements, I'll be left with upper triangle and lower triangle. And if I half the number, I'll be left with either upper triangle or lower triangle. So all the principal diagonal I can decide, and I can decide either all the upper triangle or lower triangle. And that's what is in my hand, is in my control. Which means my answer here is going to be 12 plus. This is 144 minus 12 divided by 2, which you can simply do as what? 144 minus 12. It is actually 72 minus 6. Half I already know. 72 minus 6 is how much? 66. Yes or no? And 66 plus 12 is 78. So the answer to this question is 78. How many of you understood this? Just quickly give me a thumbs up in the chat box if you all were able to process this. What did I do? I first of all gave you the idea for a 3 by 3. We developed the logic. After developing the logic, we derived a formula for an n by n. And after deriving the formula for an n by n, we came up with the answer to this question where it was a 12 by 12 matrix. Yes or no, everybody? Did you all get this? Did you all understand this? Yes or no? With this, sir, when we talk about the concept of equal matrices, what do you mean by that? Let us quickly take a 10 minutes break and then we'll resume. Is that okay? So that we can stretch it for a longer duration. So it is 9 o'clock. We'll resume at 9:10. Is that fine? So we are taking a 10 minutes break and then we'll resume at 9:10. So just a break. We'll quickly come back. So stretch yourself, take a break, and then we'll come back. This is how we'll keep taking breaks so that we can stretch this session to a great extent. Okay, so come back, everyone. The break is over. I think you had a good break, a sufficient break where you must have walked, stretched, hydrated yourself. And let's get started with this discussion. So, all you who can hear my voice, all who can, listen to my voice, come back to the desk, sit, and start watching it again. Shall we resume it? Shall we start watching it? Everyone, come back. So, here we are. When we talk about the next thing, which is said to be equality of matrices. So whenever I wish to say that two matrices are equal, that claim I can bring with the two conditions. Which two conditions? First of all, they should have the same order. They must have the same order, which means if first matrix has the order m cross n, the second matrix should also have the order m cross n. Sir, is that the necessary and the sufficient condition? Absolutely not. Then what? Then with this, the corresponding elements, each element of one matrix should be equal to the corresponding elements of other matrix. So what do you mean by that? We really didn't get that. I'll take an example. Will that be understandable? First of all, if I try and give you the mathematical definition, all I'm saying is that if there is a matrix A, there is a matrix B, and if they are said to be equal, it will be equal if they are having the same order. If they are having the same order, m cross n. Did you get the first condition? Yes or no? The second condition is all the elements A11, B11, A12, B12, A13, B13, and so on, all the corresponding elements should be equal. Then those two matrices are said to be equal. Did you understand that definition? Did you understand that statement? You will get an absolute crystal clear clarity with this example. And if you could solve this question by yourself, do write your answers in the chat box. I'll be really happy in addressing them. So the question says, for what values of x and y are the following matrices equal? So I am told that this matrix A and this matrix B are equal. So if you're in this case, these two matrices are equal, what have we just learned? Sir, we have just discussed that first of all, their order should be same. So if I look at the matrix A, 2 by 2, if I look at the matrix B, 2 by 2, so they are of the same order, yes or no? So sir, if they are of the same order, the second thing which should be matched here is that, sir, 2x plus 1 and x plus 3 should be same corresponding elements. So if 2x plus 1 is equal to x plus 3, I hope you are clearly seeing x should be equal to 2. So I think we have cracked the value of x. Second thing, sir, corresponding elements means they should also be equal, which means 3y should be equal to y square plus 2, 0 should be equal to 0, y square minus 5y should be equal to minus 6. All of these should also match, yes or no? So let's quickly start matching all of them one after another. So from this first part, 3y being y square plus 2. So y square plus 2 is equal to 3y. So can I not write it as y square minus 3y plus 2 is equal to 0? There I'll split the middle term as y square minus 2y minus y plus 2 is equal to 0. Now there is a short trick. Pay attention everyone. The short trick here says, although it's not a trick first of all, it's a simple observation. Negative of this minus 2 divided by coefficient of y square. Negative of this minus 1 divided by coefficient of y square will be my values of y. So here y is taking two values. Which two values? Plus 2 and plus 1. So there are two values 1 and 2. But this should satisfy this third equation as well. What is the third equation? The third equation is y square minus 5y is equal to minus 6. Because if this matrix, if these two matrices are equal, there is corresponding element should be same. So this element should be equal to this element, yes or no, all the participants. So with this, I have gotten another equation, y square plus 6, or rather minus 5y plus 6 is equal to 0. Now you have two choices. Either you quickly validate these two values, whether they are satisfying it or not, or you can solve this quadratic and get the answer. Getting my point? So let's quickly validate it. Shall I take 1 here first of all? So if I see 1 here, so 1 minus 5 plus 6, is it 0? Absolutely not. So 1 is not going to be an acceptable solution. Because had 1 been my value of y, it should have satisfied this condition as well as this condition. So 1 is getting satisfied for this condition, but it is not satisfying this condition. Hence, 1 will be discarded. Second value, 2. 2 square is 4. 5 into 2 is 10 plus 6, and that I think is 0. So 2 will be accepted. So I'm getting one value of x, one value of y, where x is 2 and y is also 2. And these are the two values or my answers. With this, I think for what values of x and y? 2 and 2. Everybody realized and understood how did we get the answer? How did we solve this? Everybody is able to make some sense out of it, yes or no? With this, there comes a concept which is called trace of a matrix. So what is the meaning of trace? It's a very simple, straightforward, direct concept where you simply add all the principal diagonal elements. I repeat, trace here means if you add all the principal diagonal elements, if you add all the principal diagonal elements, it is said to be the trace of that square matrix. For example, if I could simply give you a simple idea here, there is a matrix X which has 2, 3, 5, minus 1, 0, 7, 8, 4, 7. So what if I ask you the trace? Absolutely. Sum of all the principal diagonal elements. So it is 2, 0, 7. They are your leading diagonal elements, and sum of those elements is given as 2 plus 0 plus 7. So here, if I'm asked the trace of this matrix X, it is given by 2 plus 0 plus 7, which is clearly how much? 9. And that's your answer. Simple, straightforward, direct, isn't it? With this, let's see how many of you are able to solve this question. Another very beautiful, interesting, and insightful question it is. Let's see how many of you got it. So if you get the answer, do write your answer in the chat box. I'll be really happy. Or we can use the pylons feature as well. Integer type the answer is going to be. So let's see how many of you get the answer. Quickly, be quick in answering this question, everybody. How do we do it? Let's talk about that. It says, this is your matrix A. This is your matrix B. I am not told that alpha, beta, gamma are of course real. That's true. But I'm not told that matrix A and matrix B are same. Of course not. Of course not. But what I'm clearly told is that trace of A and trace of B is same. Okay, that's great. Trace of A and trace of B is same. So if I'm told trace of A, are you all not noticing that trace of A would mean the sum of these elements? Trace of B would mean sum of these principal diagonal elements. And we are told trace of A and trace of B should be same. What does it mean? Trace of A is given as alpha square plus beta square plus gamma square. Trace of B is given by 2 alpha, 2 beta, and 2 gamma minus 3 sum. So sum of principal diagonal elements of A, sum of principal diagonal elements of B. Yes or no? Everybody getting it comfortably? Yes or no? All the participants. So far, is there any confusion? With this, if I take all the terms on the left hand side, sir, why are you doing it? Have patience. So I'll write it as alpha square minus 2 alpha plus beta square minus 2 beta plus gamma square minus 2 gamma plus 3 is equal to 0. If I could rearrange it a little, what do I mean by rearranging it a little? This 3, can I not split as 1 plus 1 plus 1 whole is equal to 0? I have done nothing. I have just used the information given in the question. They told trace of A and trace of B were equal. This is trace of A is equal to trace of B rearranged. Getting my point? Now with this conclusion, if I look at a little bit of details which I'm having, pay attention everyone. If I ask you to pay attention, alpha square minus 2 alpha plus 1 square. Are you noticing A square plus B square minus 2AB? What is that? A square plus B square minus 2AB. That is A minus B whole square. So here, is it not going to be alpha minus 1 whole square? In the same fashion, if I ask you beta square minus 2 beta plus 1 square, what is it going to be? Is it not going to be A square plus B square minus 2AB? That's clearly beta minus 1 whole square. So this one I'll be writing as beta minus 1 whole square. Now the final part. The final part here says A square plus B square minus 2AB. How much is going to be a minus b whole square, but with gamma and 1 as a and b. So gamma minus 1 whole square is equal to 0. Now you tell me, what does it indicate? What does it imply? What is it suggesting to you? Is it simply not saying you a very simple observation, a very simple thing, that sir, sum of the squares of three numbers is 0? When does it happen? Sir, it happens only when the numbers are 0. Because when numbers are squared, which are real, they'll be non-negative. So if non-negative numbers are added and the sum is turning out to be 0, sir, it can happen only in one case, when all the three numbers are 0. Which means ultimately what am I getting? I am getting alpha minus 1 to be 0. I am getting beta minus 1 to be 0. And I'm getting gamma minus 1 to be 0. Because if all three of them become 0, 0 square plus 0 square plus 0 square will be 0. Everybody getting that? Yes or no? So with this, will I not reach to a conclusion that sir, alpha, beta and gamma, they all should be 1? And I think what was I asked? I was asked alpha inverse, beta inverse, gamma inverse, which means 1 upon alpha plus 1 upon beta plus 1 upon gamma. And I think if alpha, beta and gamma are 1, then 1 upon alpha, 1 upon beta, 1 upon gamma will also be 1. So 1 plus 1 plus 1 is 3. And that's your answer. How many of you marked 3 as the answer in this question? Let's quickly see. So 3 was supposed to be marked correctly by most of you. And I'm sure some of you must have done it. Yes or no? Everybody understood that whole logic, the whole concept. Great, excellent, perfect, brilliant. With this, the only expectation I have is, do you remember we have just discussed the concept of symmetric and skew-symmetric matrix? Do you remember that? Although we did discuss it in that one shot of determinants as well. With this, I hope you do remember that we have given a very simple idea that here, if there is a matrix A and if you take its transpose and if you generate the original matrix A, it is said to be symmetric. Remember that? Similarly, if there is a matrix B and if you take its transpose and if it is found to be negative of that matrix, it is said to be skew-symmetric. And when I explained you symmetric and skew-symmetric, I told you the concept of transpose. Do you remember that? Let's quickly review that. So concept of transpose says that if you interchange rows and columns of a given matrix, if you interchange rows and columns of a given matrix, do you simply not get the transpose of a matrix? If I were to take a simple example, for a matrix A, 1, 2 was its first row, 1, 2 will be its second column in its transpose. 4, 5 being the second row will become the second column in its transpose. 7, 8 being its third row will become the third column in its transpose. Simple, easy, understandable, yes or no? Few basic, clear and straightforward things. Now, if I took transpose of this, now if I take transpose of this, will I not again get this? So I hope the whole idea is really simple, that if you take transpose of transpose, you get the original matrix. Everybody, yes or no? Yes or no? The third thing, sir, trace of A transpose and trace of A is going to be same. What does this property mean? Let's quickly go through that. All I'm saying is that let's quickly build this idea here. Let's say you have a matrix X, which has elements, let's say A, B, C, and D. And I take you through the transpose of X. Of course, when I'm talking about trace, it comes with the square matrices only. So if it is a 2 by 2, its transpose will be AB becoming the first column, CD becoming the second column. Are you all clearly not noticing here that, sir, when you take trace of X, what is it going to be? Sir, it is going to be A plus D. Yes or no? Can you help me with the trace of X transpose? Can you help me with the trace of X transpose? Is it again not going to be A plus D? Because when you take the trace, A11, A22, A33, they remain same. Their position remains unchanged. Even if you interchange rows by columns or columns by row. So that's the whole idea, that whether you take trace of A transpose or trace of A, it is going to be same. Everybody remember that? Will you all remember that? The basic standard straightforward property? Yes or no? And I think something really straightforward, which we have just discussed in the previous slide as well, that if transpose of a matrix is equal to it, then it is symmetric. If transpose of a matrix is equal to negative of it, it is skew-symmetric matrix. And that's exactly what we are given over here. Everybody clearly noticing, understanding, and getting it? Yes or no, all the participants? Yes or no? I think there is no confusion so far regarding that. Determinant, I think we have already discussed. I think I need not explain that. And with this, let's solve a question. Options we are given. So let's see how many of you get it right. I'm starting a poll in which you can participate using Pylens. It's an application which you can download from Google Play Store, or if you're watching it on the laptop, you can download it from Chrome Store as well. So here we are starting this poll, and let's see how many of you genuinely get it right. Yes or no? So this is a question which says, sir, there is a matrix A asked by JEE Mains in 2024. There is a matrix A which is given by root 2, 1, minus 1, root 2. There is a matrix B which is given by 1, 0, 1, 1. There is another matrix C which is a product of A, B and A transpose. There is another matrix X which is a product of A transpose C square and A. One very beautiful property which we although have already discussed while discussing the chapter determinants, if you could remember, that if I ever ask you determinant of product of three matrices, then determinant can be distributed over them individually, which means I can write it as determinant of X into determinant of Y into determinant of Z. Not just that, determinant is such a beautiful operation here. Let's say determinant of X to the power 5 I want, or rather I take the determinant of X and then I raise it to the power 5. That is also fine. Everybody understanding that? Do you remember these properties we did discuss when we talked about the chapter determinants? Just before this video, a video on determinants got released, and in that video we did a detailed discussion of all these properties of determinants. We did cover determinant chapter comprehensively and thoroughly there. Remember that? So with this, if I take you towards this question, let's apply all those properties and get this question done. Before I start applying this question or solve this question, can you not tell me one more property that, sir, whether you take determinant of A transpose or A, it is going to be same? What did I just say? I am saying you take a matrix and you find its determinant, or you take its transpose. You take its transpose or then find its determinant. It is going to be same. Everybody getting my point? I repeat. You have a matrix, of course a square matrix, and you take its determinant, or you take its transpose and then take its determinant. It is going to be same. Shall I repeat that? All the participants, yes or no? Yes or no? So with all these things, if I apply them here in this question, we'll get the final answer. Quickly, be quick. So here, if I want to get the value of determinant A, what is it going to be? Root 2 into root 2, that's 2, minus 1 into 1, that's minus 1, so that's plus 1, so this is 3. Determinant of A we have cracked as 3. Sir, can you help us with the determinant of B as well? Yes, determinant of B is going to be 1 into 1, that's 1. 1 into 0, that's 0. So determinant of B we receive as 1. Everybody comfortably getting this? Yes or no? All the participants. With this, if I ask you C, determinant of C, because ultimately we need determinant of X. Let me come back to this place. Determinant of X I want. So determinant of X is going to be determinant of A transpose, C square and A. And we have just discussed determinant is such a beautiful operator that over product of matrices, it can be distributed, which means it is going to be determinant of A transpose into determinant of C square into determinant of A. We did discuss whether I multiply this matrix C twice and then find its determinant, or I find its determinant and then square it. It will remain same, which means I can write it as determinant of A transpose into determinant of C square into determinant of A. One more beautiful property you remember. So what is that? I hope you do remember. Sir, whether you take determinant of A or determinant of A transpose, it stays same, which means what? Determinant of A transpose, can I not write it as determinant of A? So this will be determinant of A into determinant of C square into determinant of A. So determinant of A into determinant of A is determinant of A square. Yes or no? So my whole problem boils down to this, which is determinant of A into determinant of C whole square. Sir, luckily you know one thing, which is determinant of A, which is 3. So I can substitute this 3. 3 square is 9. So here, this part I receive as, this part we have already cracked as 9 times determinant of C square. So now your problem boils down to finding the value of determinant of C. Shall you not find determinant of C? I should. But how? Let's work on that part. Determinant of C. Now let's talk about C. Sir, matrix C is given as A, B, AT. So determinant of C here will be given as determinant of ABAT. Now again, that simplest, beautiful property here. What is that? So determinant can be distributed over product of matrices. Yes, indeed. So determinant of C will be determinant of A into determinant of B into determinant of A transpose. Remember that, everyone? Yes or no? With this, sir, what do we get? Determinant of C, I'm getting very close to. Determinant of A, determinant of AT. So whether you find determinant of A or determinant of AT, we have just discussed, they both are same. So with this, I hope this determinant of A was 3. Determinant of AT is also 3. So 3 into 3, that's 9 times determinant of B. So determinant of B we have already cracked as 1. So this is 1. So 9 into 1 is clearly 9. This is not 9.1, mind you students, that's 9. Excellent. So we have gotten determinant of C as well. So if we have gotten determinant of C, I'll push it here. So determinant of C is 1, 1 square is 1. So my final answer, which is the value of determinant of X, is going to be 9 into 1 square, which is luckily nothing but 9. How many of you got 9? Did I make any mistake? Because 9 is not given in any of the options. So let me just check it once again. X was given as A transpose C square A. Oh, I'm really sorry. This is C square and C. I'm really sorry. I don't know why did I take it as this. 9 is 9 there. Determinant of X is 9 into determinant of C, which is 9. I don't know why did I take it as 1. So this is 9 square. I'm really sorry. I forgot it. So 9 square into 9 is 729. Cube of 9. And that you are given in option B. I'm really sorry for that calculation mistake. Thank you so much for that correction. And finally, you were supposed to mark option B as the correct answer. Beautiful, excellent. And I'm sure some of you must have. No worries with this. Did you get a decent clarity on this question? Did you understand the whole operation? Did you get the whole idea? How did I do it? How did I apply determinant on product of matrices? How did I apply property of determinants on transpose and a matrix? How did I apply this property here, that whether you do the power first or take the determinant later, or you take the determinant first and do the power later, it will be same. Everybody understanding this? Everybody clearly noticing this and getting it? With this, now let's talk about singular and non-singular, shall we? Everyone, pay attention here. Okay, forget this. Here we are with singular and non-singular. Everybody noticing this? Great, good, cool, nice. I hope you all remember this is also what we have discussed when we talked about the one shot of determinants, didn't we? You remember that? So if I talk about a square matrix and if I could find its determinant, and if its determinant is found to be 0, if its determinant is found to be 0, we call it singular. And if its determinant is non-zero, we call it non-singular. Remember that? A square matrix is said to be non-singular if its determinant is non-zero, and it is said to be non-singular if its determinant is non-zero, and it is said to be singular if its determinant is 0. Everybody remember that? Yes or no? I think the job is done. I think I told you this property as well, didn't I? Sir, what was this property? This property says there is a matrix A. First thing, it is a square matrix, and of course, luckily, it is a skew-symmetric. Remember that skew-symmetric? A transpose is negative of A. Yes or no? Aij is equals to minus Aji. Remember that whole thing? And its order is odd, like order 3, order 1, order 5, order 7. So odd ordered skew-symmetric matrix. Always remember its determinant is going to be 0. I think we did discuss it this one, this property. Yes or no? Remember that. So an odd ordered skew-symmetric matrix is always singular. Will you all remember that property? Yes or no, all the participants? And one thing, as we have just discussed in the previous question as well, transpose of a matrix and the matrix. Transpose of matrix, determinant or determinant of that matrix, it is going to be same in either case. Remember that, yes or no, all the participants. So let's solve both of these questions one after another. Let's solve the first one. The first question says that we need to prove that A plus AT, where A is merely a square matrix and this A plus AT is going to be a symmetric matrix. How do we prove it? Let's say, for the first question, let's say there is X which is given by A plus AT. That's what I'm assuming. I hope I can say so or do so. So with this, pay attention everyone. If I want to prove that it is symmetric, so I'll take transpose of X. So if I'm taking transpose of X, which means I'm taking transpose of A plus A transpose. Now, transpose is such a beautiful property that over addition or subtraction, it can be distributed just like that, which means here, I can say that this transpose can be distributed over this A, which means A transpose, and this transpose can be distributed over this A transpose, which is transpose of A transpose, which is A. Remember that we did discuss. Transpose of A transpose is going to be A. And with matrices, they are commutative, which means A plus A transpose plus A or A plus A transpose, it is going to be same, which is X luckily, because A plus A transpose was X. Have we not proved a simple result, a straightforward result, that transpose of X we have received as X? Transpose of a matrix we have received as the original matrix. That matrix is clearly symmetric. I think it is already proven. Yes or no, everyone? Similarly, if I talk about the matrix given in the second question, let's call it Y. So A minus A transpose, I'm calling as Y. Let's say so. How do we do it? I think it's really simple. If I take Y transpose, if I take transpose of Y, it will be written as A minus A transpose transpose. And again, the basic property here, the transpose can be distributed over addition or subtraction. So if I do so, what will I get? I'll get A transpose minus transpose of A transpose. Because over addition and subtraction, it can be distributed. With this, sir, A transpose stays like that, but transpose of A transpose is A. One thing I'm going to do, can I take negative sign common from here? So if I'm taking negative sign common, will I not be left with minus of A minus A transpose? And what is A minus A transpose? Sir, if you look at A minus A transpose, that was originally Y. So you got minus of Y. What does it imply? I hope you are clearly noticing. I begin with Y transpose and I got it as minus Y. So if transpose of Y is received as minus of Y, what does it indicate? Does it not simply mean that Y is a skew-symmetric matrix? Yes or no? So that's exactly what we were supposed to prove, that this was symmetric and this was skew-symmetric. Now, one thing I want to tell you all, something really important and crucial at this stage, which you all must remember now, is that if there is a matrix A, can I write this A as A plus A transpose plus A minus A transpose? So no, that's wrong, because A transpose and A transpose will get cancelled, but A plus A will be 2A, but on the left hand side it is A. So if I multiply this whole expression by half, which means half of A plus A transpose plus half of A minus A transpose, what does it mean? I hope you are noticing, first of all, that A transpose by 2 minus A transpose by 2 will be a null matrix, zero matrix. Remember that. And along with this, A by 2 plus A by 2 will be A. So LHS and RHS are same. But sir, why are we really doing it? What is the need of doing it? What is the point of doing it? The point is really simple, students, here, that this part here is called the symmetric part, Because as we have just proved, A plus A transpose is always symmetric for any matrix A. And even if you divide it by it, it will remain symmetric. And when you look at this part, I hope you do remember, we have just proven that A minus A transpose is skew-symmetric for any matrix A. So even half of A minus A transpose will be skew-symmetric. Sir, what does it all mean? It simply means that everybody, please pay complete attention here. Notice this part here, that there is a matrix A which can always be written as a sum of two matrices where one of them is symmetric and other one is skew-symmetric. Everybody got that? Yes or no? All the participants, be quick. I repeat, all the square matrices in the world can be written as a sum of two matrices where one of them is symmetric and the other one is skew-symmetric. Shall I move ahead from here, all the participants? Have you gotten a decent clarity on this? Yes or no, everyone? Yes or no, everyone? With this, I want to clarify a few more properties related to scalar and multiplication of matrices. What does it mean? Let's say there is a matrix A and B, and they all both are conformable for addition or subtraction. Conformable for addition or subtraction means they can be added or subtracted. Corresponding elements are added, corresponding elements are subtracted. So if their addition or subtraction is multiplied by a scalar quantity, so that can be done individually as well. That means lambda times A plus minus lambda times B. Getting it, everyone? So that scalar can be distributed like this. Not just that. Let's say there is a matrix A and you have found its trace, and then you are multiplying it by a scalar quantity. Or there was a matrix A, you multiplied by a scalar quantity, and then you are finding its trace. It is going to be same. So whether you add its principal diagonal elements and then multiply by scalar, visualize it by yourself, or you multiply that matrix by a scalar quantity and then add all the elements, will it not be same? Sir, it is. Let me prove it with a simple idea here. Let's say there is this matrix A which has elements as A11, A12, A21 and A22. Yes or no? Now, if I ask you what will be lambda A, you will say, sir, a scalar when gets multiplied to a matrix, it is pushed to all the elements of it. It is multiplied with all the elements. So there I'll be writing it as lambda A11, lambda A12, lambda A21 and lambda A22. Yes or no? Now you please help me with the trace of this lambda A. Can you? Sir, if you are asking us trace of lambda A, it will be sum of the principal diagonal elements. So it will be lambda A11 plus lambda A22. So if I take lambda common, it will be A11 plus A22. Can you help me with A11 plus A22? Yes or no? I hope everybody is noticing A11 plus A22 is trace of A. So that's exactly what you are told, lambda times trace of A. And I think we really don't have to do it like this. You are intelligent enough to visualize it like this. Yes or no? And if you are, I think this property is very well understood by you all. Everybody getting that? Now this property is again a very interesting one. Whether you multiply a matrix by a scalar, you then take its transpose, or you take its transpose first and then you multiply that by scalar. It is going to be same. It is going to be same. Can you visualize it by yourself? Just try to imagine it in your brain. Sir, whether you multiply a scalar first and then take the transpose, it doesn't matter because that scalar is there with all the elements. Or you took the transpose first and then you multiply that scalar to all the elements. It will still remain same. Yes or no, everyone? Are you able to make some sense out of this property? Is it not self-evident? Is it not self-explanatory? Are you able to make some sense out of it? Everybody, give me a quick confirmation in the chat box if you have gotten it. Now with this, the next property. This is a very beautiful property which you should remember. What does this property say? Let's say there is a question, there is a matrix, and this matrix A is given by, let's say, there is this matrix whose determinant I'm taking. So matrix A was like 2, 3, 5 and 1, right? Or let's say even whatever I take, let's say 7 here. Is that okay? So with this, I hope this is matrix A 2, 3, 5, 7. So its determinant will be what? 2 into 7, 14. 3 into 5, 15. So its determinant we receive as -1. Comfortably getting this, everyone? Yes or no? Here I'm saying you a simple fact that let's say I ask you 5 times A and then its determinant. So one of the methods could have been you multiply all the elements by 5 and then you take the determinant. Absolutely yes. But I think you do remember we did discuss this property while we were discussing the chapter determinants, don't we? Remember that? So I hope you remember. So that here, this 5 as a scalar can be taken out, raised to the power, which is the order of this matrix. So order is 2 times determinant of A. So why is it happening? Okay, let's talk about that. Matrix A here is given by 2, 3, 5, 7. So with the matrices, the beautiful thing is that if I wish to multiply it by a scalar, that means 5A if I wish to do, I'll be doing it as 5 into 2. I'll be doing it as 5 into 3. I'll be doing it as 5 into 5. And I'll be doing it as 5 into 7. So with matrices, if you do a multiplication by a scalar, that scalar gets distributed to all the elements. Remember that? But let's say now I wish to take the determinant on both these sides. So what happens when I wish to take the determinant on both these sides? Sir, it will be really simple. The determinant of 5A means determinant of 5 into 2. This is 5 into 2. This is 5 into 3. This is 5 into 5 and this is 5 into 7. This dot represents product here. So determinant of 5A. Now with the determinants, I hope you do remember in the last session, we did discuss that here from determinants, you can take elements common from any row or column. So from first row, if I take 5 common, I'll have this 5. From second row, if I take 5 common, I'll have another 5. So I'll have 5 square outside. And inside, I'm again left with 2, 3, 5, and 7. And I think I need not tell you what was 2, 3, 5, 7. 2, 3, 5, 7 was your determinant A, which finally leaves you with determinant of 5A as 5 square times determinant of A. I hope everybody is able to make some sense out of it. That, sir, here this 2 implies what? The order of that matrix. Which means, I hope now we can discuss this property very clearly, that determinant of lambda times A, where lambda is a scalar, is always given by lambda to the power n times determinant of A, where what is n? The order of that matrix. Comfortably got it or not, all the participants? Shall I move ahead from here? If you have gotten this part, this property is such a crucial and important property that you will be seeing it getting used in a lot of questions. I'm constantly telling you the importance of this chapter. IIT in mains, forget advanced for a while, in mains asks minimum 2 to 3 questions from the combination of matrices and determinants. 2 to 3 questions, almost in every single shift. 3 questions, if done properly or correctly or accurately, will fetch you 12 marks. In JEE mains, from math section, plus 12 means amazingly a lot. You know that, right? That's what I'm saying. 2 chapters, 12 marks. Can you believe the importance of this chapter? Yes or no? Shall I get back to the discussion here? So with this, if we go ahead with all what we have discussed so far, let's quickly solve a question. Another question right there in front of us. What does it say? It says, find non-zero values of x satisfying this matrix equation. So sir, if we are told that it is a matrix equation, first of all, does it match here the idea of conformability? So this is a 2 by 2 matrix. This is a 2 by 2 matrix. This is a 2 by 2 matrix. So this 2 by 2 and 2 can be added even after a multiplication by a scalar and can be compared with this. So comparison is perfectly possible. But how are we going to do that comparison? That's what we are going to discuss. But let me simplify the LHS first. So this scalar when pushed inside will make it look like what? 2x square. This is going to be 3x. This is going to be 2x here. And this is going to be x square. Yes or no? Everybody got this? I hope you are comfortably getting it. Now this 2 when pushed here. So 2 into 8 will give me a 16 here. 2 into 5x will give me 10x here. 2 into 4 will give me an 8 here. And 2 into 4 will give me an 8x here. What are we told? That, sir, these two matrices are supposed to be added. So if two matrices are supposed to be added, their corresponding elements are added. Their corresponding elements are added. The same thing I'll do with the right hand side as well. So 2 into x square plus 8 will be 2x square plus 16. 2 into 24 is clearly 48. 2 into 10, that's 20. And 2 into 6x, that's 12x. Yes or no, everybody? Got this part comfortably? Now, sir, we are told that these two matrices are equal. Indeed, they are. So their corresponding elements should be equal. So 2x square plus 16 is equals to 2x square plus 16. Will I get anything out of it? Absolutely not. But 2x plus 10x is equal to 48. So 2x plus 10 is clearly 12x is equal to 48, and 12 into 4 is 48. Yes or no? So x I receive as 4 from here. Everybody got that? Yes or no? With this, if I compare it here, 3x plus 8 being 20, I think 3x is 20 minus 8, that's 12. So x I receive as 4 from here as well. So I am following that consistency here, that I am seeing x satisfying 4 here, 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 which means x being 4 should be satisfying this relation as well. Let's quickly verify that. So it says x square plus 8x is equals to 12x. Okay, so if this part says that x square plus 8x,
सॉरी सर भूल गया था फिर याद आया
मैंने तुम्हें आवाज लगाई थी बहुत बार, तुमने सुना नहीं,
सॉरी सर
कोई बात नहीं. Just give me a moment, students. Hold on for a while. So here we are. I am saying x square plus 8x is going to be 12x. Yes or no, all the participants? So if x square plus 8x is going to be 12x, what do we get from here? We'll get two results, two conclusions. Which two conclusions? 8x goes to the other side, 12x minus 8x is 4x. So with this, I get two values of x. If I cancel this x by this x, root loss will happen. So I got to consider one of the values of x is 0. But if this x and this x are cancelled, where I'm considering x to be 0, I get other value of x as 4. But x being 0 could be an answer to this final part, but it is not satisfying this, this, and this. But 4 is something which is common to all the 4 values. 4 satisfies this, 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 and this, all 4 possibilities. So what is going to be the answer? Non-zero values of x anyways we were asked, so answer will be 4. How many of you got it? How many of you cracked it? How many of you were able to find the answer to this question like this? Do you have any other approach? If you do, kindly share. I'll be really happy. Now, with this, few things which we'll be understanding now. I hope this part makes complete sense, that if I multiply a with a, I can now write it as a square. If I multiply a with itself 3 times, I can write it as a cube. So technically, if I'm multiplying the matrix a with itself n times, I'll be writing it as a to the power n. Comfortably processing this part or not? Yes or no, everybody? Simple, straightforward, doable, and understandable. With this, do remember, if a matrix is symmetric, then its even power or its any power is always symmetric. Sir, what do you mean by that? I am saying, let's say if I am told that there is a matrix X which is symmetric. So I am told that the matrix X is symmetric. This is what I'm given. So when I'm told that matrix X is symmetric, what does it mean? So whenever I'm told that matrix X is symmetric, that means X transpose is X. That means X transpose is X. Now, I am told it's any power, any natural number. Let's say x to the power 50 I'm asked, or x to the power, let's say 27 I'm asked. So x to the power 50, I need to find out whether it is symmetric or not. So let's call it y. X to the power 50, I'm calling y for a while. So what will be y transpose? So y transpose will be x to the power 50 transpose. Now transpose is such a beautiful property again, that 50 and t can be swapped, which means here I can write it as x transpose to the power 50, which means x transpose, x was symmetric, so x transpose will be x, so it will be x to the power 50, which is y. So I repeat, I began with y transpose, but I concluded it to be y, which means y is symmetric. You can prove the same result for x to the power 27. I hope if you treat it as z, you will see that z transpose will come out as z. So shall I repeat that whole thing? That the idea is straightforward, that if X is a symmetric matrix, and if it is raised to any natural number power, then it will still remain symmetric. Did you get that? Now there comes a very beautiful property where for skew symmetric, the power matters a lot. So what do you mean by that? I want to say that let's say there is a matrix Y, and I am told that this matrix here is a skew symmetric. This matrix Y is a skew symmetric. Now in this matrix, of course, whenever somebody says it is skew symmetric, so its transpose will be negative of Y. Yes or no? Everybody, please pay attention. Now, when I talk about Y transpose, let's say I define a matrix Z, which is Y to the power n. So if I take Z transpose, which means I'm taking the transpose of Y to the power n transpose. Now, one thing we know, sir, Y n and transpose are interchangeable, which means I can write it as Y transpose whole raised to the power n. Getting it, everyone? But sir, Y transpose we have just discussed is minus Y. So this can be written as minus Y to the power n. Now it all depends on two cases. Sir, if n is even, minus 1 will be absorbed. So it will be Y to the power n. But it is happening when? Sir, when n is even. But sir, if the power is odd, minus sign will not get absorbed. So it will be minus Y to the power n. It will happen when n is odd. Sir, what do you mean by all of this? I am giving you a simplest idea here, that Y to the power n. What is Y to the power n? That was Z. So this gives me Z here. Y to the power n is Z. So this gives me minus Z here. What is the whole point? The whole point is really simple. I started with Z transpose and I got Z. When n was even. I started with Z transpose and I got minus Z. When n was odd. The whole conclusion is really simple, absolutely simple, that if Y is a skew-symmetric matrix, then Y to the power n could be symmetric or could be skew-symmetric. I hope you are able to process and develop this idea that Y to the power n will be symmetric if n is even. If n is even. Y to the power n will be symmetric as long as n is even. Y to the power n will be skew-symmetric. Y to the power n will be skew-symmetric if n is odd. So it will be skew-symmetric if n is odd. This all is happening because if the power is even, that negative sign gets absorbed, it becomes positive, it becomes Y to the power n, which was originally Z. So I got Z transpose as Z ultimately in the end. But if minus Y to the power n, for n being odd being done, then minus sign still remains outside. Y to the power n stays like Z. So Z transpose I receive as minus Z. So if Z transpose is minus Z, I need not tell you Z is an skew-symmetric matrix. Z is a skew-symmetric matrix. But why did it happen? Because their n was odd. So it all depends on n being even or odd. If I could take an example, I give you an example as well so that it becomes more understandable. Let's say I am given that there's a matrix A, which is a skew-symmetric matrix. Yes or no? So if A is a skew-symmetric matrix, I hope this is very well understood by you all, that A to the power T, I mean A transpose will be minus A. It is not power here. What do I mean all of this? I just wish to give you a very simple idea here that A transpose is minus A. So there, if I talk about A cube and if I talk about A to the power 6, you help me. A cube and A to the power 6, what are they going to be? So A cube, let's say I'm denoting by a matrix B. A to the power 6, I'm denoting by a matrix C. So here, can you help me with B transpose here? Sir, B transpose is technically nothing but what? A cube transpose. Transpose in this power can be interchanged. So there I can write it as A transpose cube. But we know A is a skew-symmetric. So A transpose will be minus A. And minus A cube, which means odd power, is minus of A cube. What is A cube? A cube was B. So it is minus of B. So I am saying that I started with B transpose and I got minus B. So what is going to be B? B is going to be Skew-Symmetric. But can I not directly generalize it now? That if A was a Skew-Symmetric and if its power is odd, it is going to be Skew-Symmetric. Second conclusion. If A is a Skew-Symmetric, but if its power is even, even means what? Here, pay attention everyone. A to the power 6 I want to talk about. So I'll take the transpose of C, which is A to the power 6. So what is C? A to the power 6, it's transpose. Transpose and power can be interchanged. So there I'll say A transpose to the power 6. What is A transpose? That's minus A. A transpose is minus A. So it will be minus A to the power 6. Now power 6 being even will absorb this negative sign. So it will leave me with A to the power 6, and A to the power 6 was originally C. So I began with C transpose and I concluded it as C, which means C or A to the power 6 is what? A symmetric matrix. Why is it all happening? Can you generalize this? So first of all, we know that A is a skew-symmetric matrix. But if A is raised to an odd power, this remains skew-symmetric. But if A is raised to an even power, it becomes symmetric. Simple, understandable, yes or no? Tell me. Yes or no? Everybody got this? Or shall I re-explain this whole idea? Everybody understood this, yes or no? Comfortably getting it? Can I move ahead from here, all the participants? With this, if you have gotten this, let us discuss one more property, or rather a few more things, so that you can clearly see this. I think we have discussed it, that if there is a matrix A which is diagonal of this, B which is diagonal of this, then their product will be diagonal of this. Let me explain it with an example. There is a matrix A which is the diagonal matrix 2, 0, 0, 1. There is another matrix B which is another diagonal matrix 3, 0, 0, and 5. Right? I hope you are paying attention. Everyone pay attention. If I ask you the product AB, so I hope matrix multiplication you know very clearly. I'll choose rows from here. I'll choose columns from here. If it is a 2 by 2 matrix, this is also a 2 by 2 matrix. So first of all, what should match is that this number of columns here and the number of rows here, they should be same. So if this 2 and this 2 are same, I can multiply these matrices. They are confirmable for matrix multiplication. Now, what does it imply? That if I choose this row 2, 0, and if I multiply this with this column 3, 0, so rows I'll choose from A, pre-factor, columns I'll choose from B, post-factor. Left, right. Understanding it? So here what I'll do is this 2 into this 3, which is 6, plus this 0 into this 0, which is 0. Did you get it? Similarly, the row will remain same, but I'll shift it to the second column now. So now what I'll do is, pay attention everyone, this 2 into this 0 will be 0, plus this 0 into this 5 will be 0. That's what we'll do. But the job is not done yet. The job has just begun. I'll choose the second row from the matrix A. And again, we'll go back to the first column from matrix B. How will the matrix multiplication take place? This 0 into this 3 will be 0, plus this 1 into this 0 will be 0. And that's what you'll add. Now, I'll multiply this row with this column now. What happens here is 0 into 0, that's 0, plus 1 into 5, that's 5. So what do I get as the final product? I get 6005. I get 6005. What does it mean? If you have noticed something really interesting, you really don't have to multiply matrices when they are diagonal matrix. Can somebody help me with that? Has anyone cracked that logic? I'll try and tell you that logic here. Pay attention, everyone. The whole logic is simply this, that here, matrix A was a diagonal matrix which has diagonal elements as 2 and 1. Remember that. Matrix B was also luckily a diagonal matrix which had the diagonal elements as 3 and 5. So all I'm saying you in terms of conclusion is that if I want matrix AB where A and B both are diagonal matrices, then matrix AB is found by diagonal of corresponding diagonal elements of A, which is 2 into 3, and another corresponding elements of diagonal A and B both, which is 1 into 5. So that's where you get it as diagonal matrix. 2 into 3 is 6, 5 into 1 is 5. And I hope you can clearly see that's exactly what we got, 6, 5. So you really don't have to multiply diagonal matrices like this ever again. I hope you got this whole product and you will apply this short technique, this formula now, and you will very clearly get the answer if I ever give you a question, for example, somewhat like this. There is a matrix X, which is a diagonal matrix, which is given by 3, 0, 0, 0, 5, 0, 0, 0, 2. There is another matrix Y, which is given by what? Let's say -1, 0, 0, 0, 5, 0, 0, 0, 4. So I hope everybody clearly noticing X and Y, both are diagonal matrices. So their product, can you not write within seconds now? XY, you really don't have to put efforts. You will say, sir, XY here is going to be 3 into -1. That's -3. 5 into 5. That's 25. And 2 into 4. That's 8. What about the other elements? Trust me, you do it by yourself, you'll find them to be 0. Isn't it straightforward, absolutely doable, clearly understandable? Everybody understood that, the whole idea of matrix multiplication with the diagonal matrices. If both of them are diagonal matrices, you're simply supposed to multiply their diagonal elements, do nothing with the non-principal diagonal elements, and there you got the product. Will you remember that? Yes or no, everybody? Shall I move ahead from here? Now the next thing, I think this is what we have just discussed. The property gives you the extension to this as well. Let's say somebody was asking me that how do we deal with the higher powers of the matrices? I'll say if you ever get something like this, let's say there is a matrix A which is given by 2, 0, 0, 5. So first of all, the moment you see this, you must have noticed that, sir, it is a diagonal matrix. It clearly is a diagonal matrix. So if it is a diagonal matrix and I'm asking you a to the power 2026, the moment you notice that it is a diagonal matrix, you really don't have to do anything. You will say that it will be 2 to the power 2026, 0, 0, 5 to the power 2026, and that's your answer. Isn't it absolutely simple, doable? Yes or no, all the participants? Did you get it? So when we deal with higher powers, if you could crack it into something like this, I think you will be done with the questions if you know this property, don't you? Getting it, everyone? So with this, if I move ahead with one more property, this is called matrix polynomial. Have patience. In the end of this session, I'll cover it totally, clearly, with utmost clarity and with a very good, decent understanding. But with this, let us understand matrix multiplication with this question so that you get more clarity. Shall we? This is a question. It has options. So let's quickly see how many of you get the correct answer. We are starting a poll and let's see how many of you get it right. So what are we asked? We are asked the product AB ultimately. So how am I going to write that product AB? What I'll do simply is I'll choose rows from A and columns from B. Sir, why? Because AB, A is the prefactor, B is the post factor. A has an order 3 by 3, B has an order 3 by 3. So number of columns in A should match with the number of rows in B. If that matches, this matrix product is possible. Now with this, how do we multiply matrices? Talk about this. This multiplies to this. So this 1 into 1 is 1 plus this 0 into -2, that's 0. This 0 into 7, that's 0. Getting it, everyone? Yes or no? Now the same row goes to the second column here. Pay attention, everyone. So this 1, 0, 0, when gets multiplied to 0, 1, minus 2. So 1 into 0, that's 0. 0 into 1, that's 0. And 0 into minus 2, that's again 0. Everybody getting that? Yes or no? Now the next thing, the same row stays there, gets multiplied to the third column and give me this element here. So what does it give me? It gives me 1 into 0, that's 0, plus this 0 into 0, that's again 0, plus this 0 into 1, that's again 0. So that's how I have defined the first row. Comfortable, everyone? Now, so to define the elements of the second row, how are we going to get that? I'll choose the second row from this matrix A, and again columns 1, 2, 3 from matrix B. How? Let's talk about that result. Pay attention, everyone. 2 into 1, that's 2. 1 into 2, 1 into minus 2, that's minus 2. And 0 into 7, that's 0. Getting it, everyone? Making some sense? Now the next part. Second row, second column. What does it give you? 2 into 0, that's 0. 1 into 1, that's 1. And 0 into minus 2, that's again 0. Able to make some sense out of it? Now the third conclusion. Second row with third column. So 2 into 0, are you noticing it? That's 0, plus 1 into 0, that's again 0, plus 0 into 1, that's again 0. Now what I'm going to do is, I now need to bring the elements of the third row as well. So to bring that, this third row will get multiplied with column 1, column 2, and column 3 of P, so that I can figure out these three elements. Everybody noticing that? So with this, I'll get this as minus 3 into 1, which is minus 3. 2 into minus 2, that is minus 4. And 1 into 7, that's plus 7. Everybody with me so far? With this. Third row, second column. Minus 3 into 0, that's 0. 2 into 1, that's 2. And 1 into minus 2, that's again minus 2. Now, third row and third column. Minus 3 into 0, that's 0. 2 into 0, that's again 0. And 1 into 1, that's plus 1. I hope there is no confusion so far on whatever we have done. Everybody comfortably getting it? All the participants? Now with this, if I start finding the values, I hope you are noticing 1 plus 0 plus 0 is 1. 0 plus 0 plus 0 is 0. 0 plus 0 plus 0 is 0. 2 minus 2 plus 0 is clearly 0. 0 plus 1 plus 0 is clearly 1. And 0 plus 0 plus 0 is 0. Getting it, everyone? Now, minus 3 minus 4 plus 7 is clearly again 0. This 0, 2 minus 2 is again 0. And there, 0, 0, 1 is again 1. So, shall I tell you what kind of matrix it is? Or you are going to tell me the answer here? Have you all noticed it very clearly? Sir, 1, 0, 0, 0, 1, 0, 0, 0, 1, that's nothing but what? An identity matrix. So the product of A and B is neither A nor B nor null. It is going to be an identity matrix, option A. And I'm sure some of you must have marked option A. Everybody, yes or no? That's good, Dhruti. That's brilliant. I'm glad you did it in almost 3 minutes. Perfect, brilliant, excellent. With this, let's try one more question. What does it say? It says there's a matrix A which has m rows and n plus 5 columns. Okay, great. Give me a second, everyone. There is another matrix B which also has m rows and 11 minus n columns. And they are telling you that AB and BA both exist. Okay, so let's try and figure something out, and then I'll come to this part where I need to prove something. Okay, how do we prove it? I am told that matrix A has this order m into n plus 5, where matrix B has the order m into 11 minus n. Yes or no? Everybody reaching to this conclusion. Now, I think we remember this whole idea that whenever we wish to multiply two matrices, and if I wish to multiply two matrices, I know that if A into B exist, sir, it will be possible only when number of columns of A and number of rows of B are same. So this gives you a data or a statement or an equation where you are concluding that this n plus 5 should be equal to this m. Everybody got this? But sir, not just this, they told you specifically that BA also exists. So what is BA? Sir, B has an order m cross 11 minus n, right? And A has an order m cross n plus 5. That is number of rows and columns. So if somebody says that BA also exists, what does it mean? Sir, it means number of columns of B and number of rows of A are going to be same. And if they are going to be same, I get one more equation. That equation is saying that, sir, 11 minus n should be equal to n. Everybody got that? Now this value of fm, which is 11 minus n, if I push here, it gives me n plus 5 is equal to 11 minus n. So n plus n is 2n. 11 minus 5 is clearly how much? 6. So that gives you n as 3. So if I push n as 3, m I receive as 11 minus 3, which is 8. So I think we have gotten these two conclusions, which are 3 and 8. That's excellent. Good students. I'm glad you're writing it correctly. That's brilliant. With this, what am I told? What am I asked? I am told that I need to prove that AB and BA are square matrices. Okay, I will. But let me simplify this first. What is going to be the order of A? I'll say that here A is m comma n plus 5. What is m? Sir, m was 8. What is n plus 5? Sir, n is 3. So 3 plus 5 is what? 8. So A is 8 by 8. What about the matrix B? Sir, matrix B has m rows. What is m? Sir, m is 8. So matrix B is also what? 8 into 11 minus n. 11 minus n is also m, that is 8. So A and B both are square matrices of order 8. So if they both are of 8 by 8, their product will also be 8 by 8. Sir, why are you saying this? I think you already know this. That if matrix A is 8 by 8, matrix B is also 8 by 8. So for matrix multiplication, the conformability says that this 8 and this 8 should be same, which is luckily same. Now, whatever I'm left with, this and this is going to be the order of AB. So product AB, which I'm going to get, is going to be of this order 8 cross 8. And 8 cross 8 is clearly a square matrix. The same opposite you could do with BA as well. What is B? B is 8 by 8. What is A? A is also 8 by 8. So if you want to ensure the conformability for matrix multiplication, you would say this 8 and this 8 should be same, which is same. So whatever I'm left with, this 8 and this 8 is going to be the product of BA. So BA is going to be what? 8 by 8. So I think we have already proven that AB and BA both are going to be square matrices. Yes or no? I'm giving you a question and leaving you with a question with a 10 minutes break, and then we'll discuss this question together. So let's take a 10 minutes break. You also hydrate yourself. You also take a break. How will you do it, Ashlesh? Can you explain this in the comments? I'll be really happy. But yes, it's doable. It's, I think, evident. But since it's the one shot, we are going from scratch. But yes, if you tell me the approach, I'll be really happy and glad. So I'm taking a 10 minutes break. We'll resume at almost 10:25 and then we'll do it. So a break I'm taking and we'll resume at 10:25. I hope it's fine. So I'll be back. Have patience, hydrate yourself, walk, stretch, and then we'll restudy. Come back, everyone. I hope you all can hear my voice. You can see me. Come back, come back, come back, everyone. Come back, everyone. So shall we get started? Shall we resume with our discussion? I hope you all can hear me, you all can see me. And we are resuming with this question here. Shall we, everyone, all the participants? I hope you had a good break, a sufficient break where you must have hydrated yourself, stretched yourself, walked a little. And if now you're away from your desk, if my voice is what you can hear or listen to, then come back, sit at your desk and start watching it. We are resuming with this session, shall we, all the participants? So here we are. I'm sure some of you are clearly visible, can clearly see me, clearly watch me, and we can resume with this amazing session. So this question here says that there is a matrix A, which is a 3 by 3 matrix, such that A into 0, 1, 0 is 0, 0, 1, A into 4, 1, 3 is 0, 1, 0, and A into 2, 1, 2 is 1, 0, 0. Then I am asked A, 2, 3. Always remember that if something like this is given to you, something really beautiful can be predicted here. If you cannot crack it or visualize it, let me demonstrate it. But of course, you should remember that result, which is going to be demonstrated to you now. Let's say there is a matrix A. So we are taking that matrix A as, I hope you can see, A11, A12, A13, A21, A22, A23, A31, A32, and A33. Now, just give me a moment. 1, 2. Now I'm given 3 results. Sir, which 3 results? Let's talk about the first result. The first result says that if A is multiplied with 0, 1, 0. Sir, if A is multiplied with 0, 1, 0, the conclusion which you are going to get is, 0, 0, 1. Right, students? Now, I hope matrix multiplication, how do we do it? Sir, idea is really simple. First of all, is this matrix multiplication really possible? Let's quickly verify this. This is a 3 by 3 matrix. This is a 3 row, 1 column matrix. So this 3 and this 3 are same. So the matrix is confirmable for matrix multiplication. With this, the product will have the order 3 cross 1. And I think we are given the order 3 rows, 1 column. So it is perfectly fine, aligned, in sync. Now, matrix multiplication, how we do? Sir, this row I'll choose, multiply with this column. I hope you remember that. So product which we are going to get is going to be, I hope you remember, A11 into 0 is 0, A12 into 1 is A12, A13 into 0 is 0. So there I'll receive it as A12. So I'm sure most of you must have started getting this whole idea, what I'm trying to give you here. The second thing, pay attention everyone. What I'll choose here is the second row will again get multiplied with this column. So I hope now you must have built the idea. You must have gotten that sense. Sir, A21 into 0 is 0. A22 into 1 is A22 plus A23 into 0 is 0. So that leaves you with A22. So I think you already have reached to a conclusion that, sir, we really don't have to do all this to reach to A through 3. But even if you are confused, I'll demonstrate it totally. But you really don't have to. If you are a JEE aspirant, you really don't have to. So if I multiply this third row with this column again, what am I going to get? A31 into 0, that's 0. A32 into 1, that's A32. A33 into 0 is this. So I receive A32. But sir, we were asked A23. So this is not going to help us anyways, because here if I compare it, and let's say if I am asked what is A12, I would have said 0. A22, I would have said 0. A32, I would have said 1. Understanding it totally, completely, and absolutely, yes or no? So if this part is leaving us with this, let us reach to a conclusion that, sir, if you want A23, I think this and this might give you. So let's talk about that second conclusion, but this is not helping us at all. But yes, we have gotten certain values which might, but let's move towards the next conclusion. The next conclusion says that this part multiplied with the column 413. So as we have just verified that confirmability is there, so this matrix product is also fine. And 413 when multiplied, it leads you towards 0, 1, 0. Everyone getting that? Yes or no, all the participants? Thank you, Ajay. Now, shall I move ahead from here, all the participants? if you have gotten a decent clarity on whatever we have discussed so far. With this, I hope now you know matrix multiplication very easily. A11, A12, A13 with 413. I think that will be huge and that will be absolutely useless for us because I won't get or reach anywhere. So let's avoid doing that matrix multiplication. But this matrix multiplication could be a little useful because there, if A21, A22 and A23 are multiplied with 413, what do I get? Let me talk about that result. So first result I'm not writing deliberately. If you want, you could have. How? Although it is not useful, but still if you want, let me write it. Let me write it. A11, A12, A13 with multiplied with 413. So A11 into 4 would have been 4A11 plus A12 into 1. That would have been A12. And with this, the next result. Thank you, Vijay. The next result will give me what? The next result will be A13 into 3. That's 3A13. Getting it or not? All the participants. Everybody with me. But that I think is not very useful. So you should have simply avoided it. But the second result which I'm going to take is A21, A22, A23 multiplied with 413. So A21 into 4, that leaves you with 4A21 plus A22 into 1, that leaves you with A22. And the third result, A23 into 3, that's 3 times A23. And that could be a little useful because now I'm getting closer to an equation getting formed related to A23. So one data I'm receiving, which is what? This one. And is it anyways helping us? I think because A22 and A21 if I know, A22 and A21 if I know, I think I'll get very close to this answer. So here, one equation which I'm receiving is this. Sir, 4A1 plus A22 plus A23, sorry, 3 times A23, we have cracked as 1 because they are equal corresponding elements. Yes or no? This we have cracked as 1. So if we have cracked this as 1, I think you know that sir A22 was 0. A22 was 0, and if A22 was 0, this vanishes. So it leaves you with one equation, which is 4A1, which is 4A21. I'm really sorry. 4A21 plus 3A23 is 1. But sir, we are still stuck. Where? We are stuck that sir, we needed A23, but we are still having one more variable A21. Can we crack it? Let's try and do it. So with this third equation, can I crack it? The moment I try to crack it, you could have performed one more operation on A31, A32, A33 getting multiplied to 413. You would have gotten one more equation. But I think instead of that, if I work on this third result, I think it will be really beneficial. This third result, pay attention everyone. 2, 1, 2. It gives you 2, 1, 2. And this product we receive as 1, 0, 0. I'll straight away ask you to jump to the conclusion where you are multiplying this row with this column and you're comparing it with this element. Are you understanding my logic? I hope you really don't have to multiply the other elements. If you are a JEE aspirant, you really don't have to. If you are preparing for boards, you'll have to do it completely. So if you are a JEE aspirant, what will you do? A21 into 2, that's 2A1, 2A21, right? Then A22 into 1, that's A22 plus A23 into 2, that's 2A23. I hope it's visible. That's 2A23. I hope it's visible to everyone. So now what? Now I'll say if these matrices are equal, their corresponding element should be equal. So this leads you towards this conclusion. What is this conclusion saying? This conclusion is saying 0 is equal to 2A21 plus A22. I think I do remember we have cracked that A22 was 0. So if A22 was 0, I can substitute A22 as 0. Then I'm left with 2A23. 2A23. So this is what I'm receiving as 0. And there I conclude that 2 is taken common. So A21 plus A23 is 0. So A21 is minus A23. A21 is minus A23. A21 is minus A23. So if A21 here is replaced by minus A23, so this is minus 4 A23 plus 3A23 is equal to 1. Getting it, everyone? So with this, minus 4 plus 3 is minus 1. So A23 is equal to minus 1. got this conclusion, all the participants. So I think the answer should have been -1. You really don't have to do a lot of things, which I have done just to show you that this is not how you should do it. Ultimately, what do you want? You want 8, 2, 3, which you will find either by the third column or the second row. So had you just multiplied the second row with this column, and this column, you could have gotten 3 equations and 3 variables, A21, A22 and A23. So 3 variables, 3 equations. You know how to find the answer, yes or no? Understanding this result, did you understand the whole solution? Did you find that question was absolutely simple, doable, if you just simply apply the right steps and the question will be done? Shall I move ahead from here, all the participants? Did you get a decent clarity on this? Now, few properties which I think will understand one after another. Matrix product is not necessarily commutative. So what does it mean? It means, let's say if you are given product of AB and if you are given product of BA. So first of all, with matrices, this is not even possible that if AB exists, then BA will also exist. Or if BA exists, then AB will also exist. So the existence is not sure. How can you say that their product is going to be same? I repeat, let's say matrix A is of the order 3 cross 2, matrix B is of the order 2 cross 3. So are they confirmable for the product? I'll say if this 2 and this 2 is same, their matrix product is possible, and AB will have the order 3 cross 3. AB will be of the order 3 cross 3. Okay. Let's talk about BA. So sir, is BA possible? Let's see. So B was 2 by 3. A was 3 by 2. So is BA possible? Let's check it. Sir, for BA to exist, this 3 and this 3 should be same, which is same. And product of BA will be 2 by 2. So product of BA will be 2 by 2. Now, luckily, the product exists, which means AB and BA both exist. But sir, do you not think for their comparison, AB is of the order 3 by 3, BA is of the order 2 by 2? Clearly, they cannot be compared. So always remember, AB and BA will always necessarily exist. That also not true. So their comparison, whether they'll be equal or not, is not going to be necessarily true. My whole point is absolutely simple, that product of two matrices is not commutative. So if you find AB and if you claim BA is same, no, that's not necessarily true. That's not necessarily true. In some cases you may find, but that's some specific cases, so that cannot be generalized. So always remember, matrix product is not commutative. That's exactly what we have tried explaining here. Yes or no? Yes or no? Everybody got this? I hope no confusion regarding this. For example, here, matrix A is given by 1, 2, 3, 1, minus 3, 1. Matrix B is given by 0, 1, minus 2, minus 1. So if I take a row from matrix A and column from matrix B, I hope you're understanding 1 into 0. AB I'm defining. 1 into 0 is 0. 2 into minus 2 is minus 4. Noticing it? Second element. 1 into 2. 1, 2 with 1 minus 1. So 1 into 1, 1. 2 into minus 1, minus 2. So 1 minus 2 is minus 1. Then I'll take second row with this column. So it will give me minus 3, 1, 0, 2. Minus 3 into 0, 0. 1 into minus 2 is minus 2. So 0 minus 2 is minus 2. Then again take the second row with this second column. So I'll have minus 3 into 1 and 1 into minus 1. So minus 3 into 1 is minus 3 and this is minus 1. Minus 3 minus 1 is minus 4. So this is how I got AB. Now if I ask you to find BA, I hope you know how to find BA. And if you find it, you will see, despite A and B both being 2 by 2, 2 by 2, their product was 2 by 2, 2 by 2. They were still not same, and that is going to happen. So I hope you are able to process this whole part. But one beautiful fact here is that identity matrix behaves as one in the world of matrices. Which means if you have a matrix A, if you're multiplying it by an identity matrix, pre-multiplication or post-multiplication, pre means I is multiplied from the left hand side to A, or if post-multiplication means I is multiplied from the right hand side, it will always give you the original matrix. That's the beauty of an identity matrix. Confirmability should be assumed, which means matrix product should be possible. Getting my point, everyone? Similarly, one more thing, O or null matrix or empty matrix behaves as 0 in the world of matrices, which means if a matrix is post multiplied by a null, or if a matrix is pre-multiplied by a null, it is going to generate a null matrix. Null matrix means, do you remember that? 0, 0, 0, all the entries are 0, 0, 0. Remember that? Again, confirmability for matrix product should be possible. Then only this all is being said. I mean, product of matrix should be possible. If that's not possible, you really won't be able to say something like that. Something really interesting is both matrices A and B are if diagonal, then only A, B and B are equal. Can you prove that very quickly? Do you remember that? I think some of you must have, who have been watching it sincerely since the beginning. If matrix A is given by, let's say, diagonal 3, 2, 5. If matrix B is, let's say, given by diagonal 2, 7, 2, then how will you define AB? Sir, AB will be given by diagonal 3 into 2, that's 6, 2 into 7, that's 14, and 5 into 2, that's 10. How will you define BA? Sir, BA will be given by diagonal, I hope you remember, 2 into 3, 6, 7 into 2, that's 14, and 2 into 5, that's 10. So in that case, that specific case, if A and B both are diagonal matrices, I hope you remember diagonal matrices. So their product will be product of their corresponding diagonal elements, other will be 0. So product is also diagonal. So in that case, whether you find AB or BA, that's luckily same. That's coincidentally same. Everybody is going to remember that result, yes or no? All the participants, give me a quick confirmation. So far, is there any confusion? So yes, few conclusions, few results. A plus B whole square in the world of matrices is not A square plus B square plus 2AB. Absolutely not. I hope everybody is clearly noticing that A into A is A square, A into B is AB, B into A is BA, and B into B is B square. So I'll have AB and BA separately because they are not same. You wouldn't say that AB plus BA will be 2AB. Absolutely not. Yes or no? Similarly, if you want to say that A plus B whole square is equal to A square plus B square plus 2AB, that will happen only if AB and BA are equal. And that's not necessarily true. Yes or no, all the participants? Now, the next conclusion. Pay attention, everyone. The binomial expansion, those who were in the beginning were asking, sir, how do we deal with the higher powers of the matrices? There comes the interesting part. Pay attention, everyone. You can always apply the binomial expansion here. What does binomial expansion say? Let's say A plus B to the power n, where A and B are matrices, n is a natural number. So if I were to apply the binomial expansion here, how will that take place? Let's talk about it. So first of all, you write nc0, remember that. Then you write A to the power n, and then you write B to the power 0. Then you write nc1, then you write A to the power n minus 1, and then you write B to the power 1. Remember that. Then you write nc2, A to the power n minus 2, B to the power 2, and so on. Ultimately, you reach to the last term, which is ncn, A to the power 0, and B to the power n. And I am not violating any law of matrix multiplication, pre-multiplication, post-multiplication, left multiplication, right multiplication. I'm taking care of the order and everything. And if you wish to apply this binomial expansion on matrix, you can. And that's how you deal with the higher powers. Sir, how we are still not getting it? I am telling you, pay attention, everyone. Have patience. The whole idea is really simple. Let's say if I were to ever deal with, let's say A plus an identity matrix raised to the power 20. That's the idea. So let's say if I'm given a matrix B and I need to find B to the power 20. So first of all, what you'll do is B into B, B square, B into B into B, that is B square into B. Let's say you do B cube, then B square into B square, you find B to the power 4. And then you start seeing a pattern, then you start seeing a generalization, and there you generalize in terms of N. That's absolutely a good idea. But what if I tell you something else? So what is that something else? If you are ever given a matrix B, you write or try to write that matrix as a sum of a matrix plus an identity matrix. So how are we going to break it or split it? First of all, write an identity matrix. Plus, think of a matrix which when added to that identity matrix will generate B. Can you not develop that idea? You know that, right? You know that. So if I could think of a matrix which when added to an identity matrix gives you the given matrix which is given in the question, and that matrix is raised to a certain higher power. So that B, first of all, I'm able to write as A plus I. For example, just to make it understandable, let's say I'm given a matrix B as 2, 3, 4, 1. So can I write this matrix B as something plus an identity matrix? Identity matrix, as we know, 1, 0, 0, 1. and this 1 0 0 1. So 1 plus something should be 2, I think 1. 0 plus something should be 3, I think 3. 0 plus something should be 4, I think 4. 1 plus something should be 1, I think 0. So I hope you're understanding. That's what I'm talking about. That when I wish to write B as a sum of two matrices, so this matrix is A and this matrix is I. That's all what I'm saying. That's all what I'm suggesting. Sir, but what is going to be the advantage of it? I'll show you with questions, don't worry. But let's learn this art of splitting a matrix as the sum of two matrices, where it is written as a matrix plus an identity matrix. Can we do so first of all? Getting everyone, getting it or not, all the participants? Give me a quick response. With this, if I could tell you a few more things. Sir, what are those things? Let's apply binomial expansion. So what does binomial expansion say? Either A plus I or I plus AI do. I hope it's perfectly understandable. So I hope you remember 1 plus x to the power n. Remember that? 1 plus x to the power n goes with this nc0. Of course, identity matrix raised to any power will give you identity matrix, because identity matrix behaves as 1 in the world of matrices. So identity matrix, no matter how many times multiplied with itself or even with any matrix, will give you that original matrix only. So there is no point of introducing an identity matrix like 1 in the world of matrices. So there is no point of writing 1 as a product. So there, 20C0, then I'll write it as a to the power 0. But of course, a to the power 0 will be null, will be nothing. But here, I mean it will be nothing, but this nothing, I'm really sorry, it's not null. A to the power 0 is like identity matrix. So this 20C0 is 1. So scalar into identity matrix will leave you with I here. So 20C0 into a to the power 0 is I. Then the next thing will be 20C1, I to the power 19. So identity matrix raised to any power doesn't matter. And then I'll be left with a to the power 1. So this is a. Then I'll write it as 20C2, a square. Then I'll write it as 20C3, a cube, and so on, and so on. Ultimately, I write the last term 20C20, a to the power 20. So do you really not think that this is also going to be really lengthy? What have you attained or achieved by splitting this matrix B into a sum of two matrices A and I? What have you attained? Trust me. With this, the question will be set in such a manner that you will get somewhat these kind of results. So what kind of results? Possibility that maybe you get a cube as null, which means a to the power 4, a to the power 5, and all the higher powers of a will be null. So all these terms will vanish. Or maybe you get a square as I. So if a square is I, a cube, a to the power 4, a to the power 5 also can be worked out very easily. And with that also, you can simplify this result. And that's how the question will be set. So my whole point is really simple. Always remember this as a fact, that whenever you are asked to raise this any matrix to a higher power, then try to split that matrix as a sum of two matrices, where one of the matrix is identity matrix and the other matrix is the summation, which you can find by simple calculation, which we have just discussed. And now if you apply the binomial expansion, trust me, your question will be simplified into something really straightforward. Everybody getting it? Yes or no? Or shall I re-explain that whole thing? Give me a quick update. Everybody with me? Any confusion so far regarding anything? So with this, I think this is all I was explaining. Now, one beautiful thing is there with matrix multiplication is it is associative. What does it mean? Let's say I want to multiply three matrices A, B, and C. Confirmability is there, which means product is possible. Now with this, the beautiful thing here is that, sir, whether you multiply BC first and then multiply it by A, pre-multiplication, or you multiply AB first and then do a post multiplication by C, it will generate the same output. But remember this, matrix multiplication should be possible. That means that confirmability, that we verify rows in columns, that should be matched. If that is not fulfilled, there is no point of discussing associativeness. Getting my point, everyone? Similarly, matrix multiplication is distributive as well, which means, let's say, sir, if you are adding B and C, and then you are pre-multiplying it by A, or rather, you pre-multiply A to B and C, that means A on the left, and then add them up. It will give you the same result. I hope these two properties are very well understood by everyone. So distributiveness and associativeness exist with the matrix multiplication as well. One thing you should remember is that there exists, let's say, two matrices whose product is a null matrix. It is not zero, it is a null matrix. Then it is absolutely not necessary that either one of them or both of them are going to be null. Absolutely not necessary. In the world of numbers, we say that if product of two numbers is zero, we say either any of them or both of them are zero, right? But in the world of matrices, we don't talk like that. We don't speak like that. Why? Let me demonstrate it with an example. This is a matrix A, which is non-null because not all the entries are zero. This is matrix B, which is also non-null because not all the entries are zero. But even if you find the product AB, you are finding it to be null. Despite getting the product AB as null, I am clearly noticing that neither A nor B is null. That whole thing, are you able to process it? Yes or no? But one interesting thing, if I could tell you, that's even a more interesting property here. Remember this as a property that let's say two matrices are there and their product is a null matrix. So what does it imply? It implies that it is not necessary that either A or B will be null. I hope this part is very well understood by you all. But I'm going to tell you something really interesting. Pay attention everyone. If you are getting A into B as null matrix, if I take determinant on both sides, so determinant of AB will be determinant of null. Now we know determinant can be distributed over product. So determinant of AB I can write as determinant of A into determinant of B is equal to determinant of null. Null matrix means what? All the entries are zero. Square matrix it is going to be because we are operating on square matrices only. So this square matrix, which has all the entries as zero, its determinant is going to be zero. So this is a zero here. Now look at this. Matrices could be anything and their product could be null, despite neither of them being null. But my whole conclusion boils down to this fact that understand this, determinant finally gives you a value, a number. So a number into another number is zero. So we are into the world of numbers now. So if a number is multiplied with another number and it is generating zero, when does it happen? So it happens only when either or both of them are zero. So that's where I'll conclude that either determinant of A or determinant of B is zero. And when I say either means both is also fine. That means either A or B or both could also be zero. What I'm trying to make you understand is, pay attention everyone and remember this as a fact, that if product of two matrices is null, product of two matrices is null. If you ever see product of two matrices to be null, then always remember either A or B is singular. Do you remember that singular matrix? Singular matrix means the determinant of that matrix is zero. Remember that. So if product of two matrices is null, that means determinant of any of them or both of them could be zero. And if that is true, that means the matrix is singular. Yes or no? Do you all remember that whole thing which we have discussed? I hope there is no confusion so far regarding all what we have discussed. All the participants listening, understanding and watching it clearly with utmost clarity. Shall I move ahead from here? Yes or no? With this, if I talk about few more things. Cancellation law does not hold, although I'll explain it with an example, but you cannot just cancel. Which means if some of you could be thinking that with matrices, if A is multiplied from the left-hand side, so this A and this A can be cancelled and we'll be left with B and C, then you are again wrong. Pay attention everyone. Not necessarily it holds, which means, let's say here, this is matrix A, this is matrix B, and this is matrix C. So I am trying to tell you that despite keeping B and C non-equal, I can ensure that AB and AC are found to be same. Did you get my point? So even if B and C were not same, AB and AC, the whole product was found to be same, then I can clearly say that if I'm given AB is equal to AC, then it is not necessarily true that B will be equal to C. Getting my point? It is not necessarily true. Yes or no? Everybody getting that fact? Yes or no, all the participants? This property holds if A is an invertible matrix. Invertible means its inverse can be found. So what is the meaning of inverse of a function, inverse of a matrix? Inverse of a matrix here means that its inverse can be found. That I'll discuss in the upcoming slides, don't worry. But for the existence of inverse, the matrix should be non-singular. So what are you saying? It is absolutely non-understandable. Whatever you're saying is going above our head. Pay attention, everyone. All I'm saying is that if you find determinant of A, in this case, 1 into 0, 0, 1 into 0 into 0 is 0. So determinant of A is 0, which means A is a singular matrix. So if A is a singular matrix, it means A is non-invertible. A is non-invertible, which means A's inverse cannot be found. I repeat, I'll explain this in the upcoming slides. For the existence of the inverse of a matrix, its determinant should be non-zero. But here in this case, if determinant A was found to be 0, I just cannot do this thing that, sir, AB is given as AC. Then you may say that A inverse into AB is equal to A inverse into AC. So A inverse into A inverse into A is identity. So this leads you B and C equal. I could have done this. I could have said this. This is perfectly a normal process. You could have performed it, but there is a catch that, sir, this whole thing which you have done, that you have pre-multiplied both the sides by A inverse, you just cannot do it in this question because A is non-singular, which means A's determinant is 0. And if determinant of a matrix is 0, its inverse cannot be found. So if its inverse cannot be found, how can you multiply both the sides by inverse? Shall I repeat that? Everybody got this logic. Everybody understood this logic. I am saying cancellation law may hold, but only when that inverse exists. And if that inverse doesn't exist, how can you just cancel it out? So you need to ensure that A inverse exists. If A inverse exists, then I could have done it. That I could have multiplied both these sides by A inverse. So A inverse into A becomes identity. Identity to B is B. Identity to C is C. So B is equal to C. That's what I could have said. But this I'll say only when A inverse exists. And in this example, A inverse doesn't exist because determinant of A is 0. And if the determinant of A is 0, your matrix inverse cannot be found. I'll tell you in the upcoming slides why. So here I am telling you one more fact, a very interesting fact. I'll simply give you this whole idea. Let's say there is a matrix A, which is given as 2, 3, 7, 5. There is another matrix B, which is given by, let's say, 1, 0, 2, 4. But let's keep it as 3, right? I hope it's fine. So now I'm asking you to find two things, product AB and product BA. Can you help me with these two products? So if I ask you to find product AB, what would that be? I hope you know it. 2, 3 with 1, 2. So 2, 3 with 1, 2. 2 into 1, 2. 3 into 2, 6. 6 plus 2, 8. 2, 3 with 3, 4. So 2 into 3, 6. 4 into 3, 12. 6 plus 12 is what? 18. Then 7, 5 with 1, 2. So 7 plus 10. That is 17. 7, 5 with 3, 4. So 7 into 3, 21. 5 into 4, 20. 20 plus 21 is 41. Now, can you help me with BA as well? How will you find BA? So to find BA, I'll do this. What? I'll multiply its rows with its columns. I hope you're able to visualize it now. Yes or no? So with this, 1, 3 with 2, 7. I hope you're noticing rows from here, columns from here. So 1, 3 with 2, 7. So 1 into 2, 2. 3 into 7, 21. 21 plus 2 is 23. Getting it, everyone? Then I'll keep the same row, but the next column. So 1, 3 with 3, 5. So 1 into 3, 3. 3 into 5 is 15. So 3 plus 15, that's 18. Pay attention, everyone. I'm going to reveal something really interesting here at this stage. Now I'll take the second row, first column again. So 2, 4 with 2, 7. So 2 into 2, 4. 4 into 7 is 28. 28 plus 4 is clearly 32. Now 2, 4 with this second column. So 2 into 3, 6. 5 into 4 is 20. 2 into 3, 6, 5 into 4 is 20, 20 plus 6 is 26. Sir, why are we doing this? Have patience. I'm going to reveal something really interesting. Pay attention first of all. I did not say this at all, that diagonal elements of AB and diagonal elements of BA will be same, and they clearly are not. But one beautiful which is happening here is that whether you find trace of AB or whether you find trace of BA, something really interesting is going to happen is, pay attention everyone, trace of AB, 8 plus 41, how much is that? 49. Trace of BA, 23 plus 26, that's again 49. Did you notice something really beautiful and interesting? What did I just say? I told you that it is not necessarily true that AB and BA will be same. Never I told you this, that sir, their diagonal elements will be same. But one thing which is going to be true for square matrices is that when you find AB and when you find BA, not even their corresponding diagonal elements will be same. No, I did not say this. But one thing is sure, pay attention everyone, their trace of AB or trace of B is going to be same. Isn't it again beautiful and interesting? Have you all understood this? So if you are ever supposed to deal with this particular property in a question, remember this, that trace of AB and trace of BA are same. I did not say principal diagonal elements of AB and principal diagonal elements of BA are going to be same. No, I did not say so. I did not say so. But what I'm saying is that sum of principal diagonal elements of AB, sum of principal diagonal elements of BA is going to be same. Everybody got that? One more very interesting property is this reversal law. So transpose reverses the order. So what does it mean? Let's say I have a product of 4 matrices A, B, C, D, and I'm willing to take the transpose of their product. So either you multiply all the 4 matrices and then they take the transpose, or you reverse the order, which means you take their individual transposes, and then multiply them, but with their orders reversed. Which means D transpose into C transpose into B transpose into A transpose. If you do with that also, you will get to the same conclusion. Everybody understanding this whole idea? Everybody understanding this whole thing? Yes or no? All the participants. Everybody built a good idea, a good logic, a good conceptual understanding around this. With this, I think this is what we have just already discussed. I told you the determinant is distributable over product of matrices. So A into B into C, and then you're taking its determinant, or if you take determinant of A into determinant of B into determinant of C, it is going to be C. Yes or no? Remember that result, that whole idea which we developed. Paying attention everyone. With this, let's try and solve this question, shall we? So I am told first of all that A is a square matrix. Okay. Then I need to find that AAT and ATA are symmetric. Okay, shall we? So here I'm just simply taking this result that I'm assuming AAT as X. Can I do so? So if this is X, just to check its transpose or not, I'll take its transpose. Just to check it's symmetric or not, I'll take its transpose. So I'll take the transpose of AAT. Yes or no? So what we have just discussed was that, sir, if you are taking transpose over product of matrices, the order reverses, the order gets swapped. So here I'll take transpose of A transpose. I'll take transpose of A transpose into A transpose. The order swaps. A into B transpose is B transpose A transpose. That's exactly what I'm saying. I hope you remember one more property here, that transpose of transpose. Transpose of transpose gives you the original matrix. So this gives you A, maybe 1 or 2 more hours. I'll stretch it because I want to complete it thoroughly. So I don't want to leave in between. So we'll be covering the entire chapter matrices thoroughly up to a great extent. Theoretically, comprehensively, I'll try to cover all the aspects. But yes, sir, one-shots are sufficient to cover or to take us towards JEE mains or advanced level? Of course not. They are never. One-shots are never sufficient. Why? Because with one-shots, you just learn and understand most of the theory. But to get more clarity on questions, to get more better understanding or deeper understanding, you need to solve more PYQs. I'll simply suggest that solve 2020 to 2026 JEE mains PYQs. They are always sufficient. And once you have mastered JEE mains PYQs, go to JEE advanced PYQs from 2000 to 2026, last 26 years. Trust me, this is always sufficient. Coming back to the discussion, I repeat, transpose of transpose is always the original matrix as we have just discussed, and this leaves you with A transpose. So this is AAT. Sir, I think AAT was X. So what did I get? Sir, what we got was that when I took X transpose, I got X. What was X? AAT. So if X transpose is X, we conclude that X is what? X is a symmetric matrix. I think that's exactly what we were supposed to prove. So if I have proven this, can I give this part as a homework to you? Will you try this by yourself? I hope. Yes or no? Will you do it by yourself? Yes or no? I hope you are clearly. You can, you should, if you want better clarity on matrices. Why should you not? Shall we try a question in that case? Shall we? What does it say? It says A and B are any two 3x3 matrices. Cool. Great. I am told that A is symmetric and B is skew-symmetric. The moment somebody says that A is symmetric, what is the meaning of A being symmetric? So if A is symmetric, that means A transpose is A. That's what I know. B is skew-symmetric, that means what? B transpose will be minus B. I think this is what we have already discussed a lot, many times, haven't we? Everybody. So with this, we are asked, sir, what is your opinion on AB minus BA? Okay, let's try and work it out. So for this category of questions, what I personally believe is, let's take AB minus BA as X. Can I take it like this? AB minus BA as X. So if I'm taking AB minus BA as X and I want to put my comment on whether it is symmetric or skew-symmetric, what I'll do is I'll take its transpose. So if I take its transpose, I'm doing AB minus BA whole transpose. Now, one thing we clearly know, remember, is that transpose can be distributed over addition or subtraction. You try it for a minute. Let me have just water and then we'll resume it. Just give me 2 minutes. Okay, so coming back to the discussion we all were having, here we are. I am saying that AB minus B I'm assuming as X. So I am saying let's take the transpose of X. So I'm saying AB minus BA transpose. Now what we know is, sir, over addition or subtraction, transpose can be distributed just like that, which means here I could have written it like the transpose of AB minus the transpose of BA. That's the beauty of transpose. It can be distributed. Now, with this, pay attention everyone. Here, what are we dealing with? Sir, we are dealing with X transpose. Technically, we are reaching to a conclusion towards X transpose. Transpose over product swaps the order, reverses the order. So if it is A, B transpose, and if I distribute this transpose over product, I'll get it as B transpose, A transpose minus. Similarly, B A transpose will be written as A transpose B transpose. The order swaps, the order reverses. So it will be A transpose B transpose. Everybody comfortably getting this too? Now with this, sir, what is B transpose? B transpose is minus B, so I'll write minus B. What is A transpose? That's A because B was skew-symmetric, A was symmetric. Here, what is A transpose? Sir, A is symmetric, so A transpose will be A. What is B transpose? B transpose is minus B, so minus of minus B will be plus B. So ultimately, what did I get? Sir, we got AB minus BA. Let me check it. I think AB minus BA was X. AB minus BA was X. So sir, you started with X transpose and that we proved as X. That means this, if I treat as X, its transpose was this only. So if transpose of a matrix is the original matrix, then that matrix is said to be a symmetric matrix. How many of you got option C? Yes or no? Everybody understood this particular part. Everybody got this. That how did we prove it? Every single step of this question. How many of you were able to crack it like this? How many of you were able to think like this? And whenever you deal with questions based on symmetric or skew-symmetric, will you be able to process it like this? Yes or no? All the participants. Shall I move ahead from here? Now, There are some different more types of matrices which I was mentioning or talking about, that when you deal with higher powers of matrices, there comes a very interesting, very amazing concept there, that orthogonal, idempotent, nilpotent, these kind of matrices are introduced. And with these kind of matrices like periodic matrix and all, your whole problem becomes amazingly simpler. How? Let's begin that whole discussion with a matrix with orthogonal. What is the meaning of a matrix being orthogonal? I'll come back to this slide, but I want to discuss something really interesting and something very beautiful with you all. What is the context of orthogonal matrices? Let's say there is a vector. So you were teaching matrices. Why are we having vectors? Have patience. Let's say vector A is given by A1 I cap plus A2 j cap. There is one more vector B which is given by B1 I cap plus B2 j cap. Now, pay attention everyone. If I just write a matrix for a while and denote it by X, and in this matrix I'm writing these elements, which elements A1, A2, B1 and B2, just doing it for a while, have patience. And I'm finding its transpose. So its transpose will be given by what? Rows into columns. So A1, A2 will become first column, B1, B2 will become second column. Yes or no? All the participants. Now I'm asking you one thing here, that let's say this x into xt, can you do? Okay, let's try and do it. So x tends to xt, what will it give me? So rows from here, columns from here. So a1 into a1, a2 into a2, that is a1 square plus a2 square. Then rows from here, columns from here. So a1 b1, a2 b2, yes or no? So next thing will be a1 b1 plus a2 b2. Now the next thing, pay attention everyone. Rows from here, column from here. So b1 a1 plus b2 a2. Can I not write it as a1 b1 plus a2 b2 only? Then rows from here, columns from here. So b1 b1, b2 b2. That is what? b1 square plus b2 square. Yes or no? Everybody with me so far, whatever I'm doing. Sir, why are you doing all this? Have patience. Let me say few more things. Which few more things? Let us say I am given that vector A and vector B are unit vectors. Unit vectors. So what do you mean by unit vectors? Sir, unit vector means vector A's magnitude and vector B's magnitude will be 1. What is the magnitude of vector A? Sir, magnitude, thank you, Vijay. Magnitude of vector A will be given by what? I hope you know that. If I'm given something like this, what do you mean by magnitude of vector A? I'm really sorry. Magnitude of vector A will be given by under root over A1 square plus A2 square. Yes or no? Sir, what do you mean by magnitude of vector B? Sir, magnitude of vector B will be given by under root over B1 square plus B2 square. Yes or no? But sir, what are we told? We are told that vector A and vector B are unit vectors. So if they are unit vectors, this whole thing is going to be 1. And this whole thing is also going to be 1. So if they both are 1, their squares will also be 1. So will I not conclude that, sir, a1 square plus a2 square is 1, and so b1 square plus b2 square? Have you understood this part? So here, if I wish to define this xt in a more better format, will I not say that, sir, first of all, a1 square plus a2 square can be replaced by 1. b1 square plus b2 square can also be replaced by 1. But let me stretch it further. I want to tell you something really interesting here. What is that thing? Here, let us say they are not merely unit vectors, but they are mutually perpendicular. Unit and mutually perpendicular vectors. So what do you mean by mutually perpendicular? Sir, when you say or claim that A and B are mutually perpendicular, that means you are saying their dot product will be 0. I hope this is what you must have studied in physics, haven't you? So if they are mutually perpendicular vectors, A dot B will be 0. So what is going to be A dot B? I think dot product in component form is given by A1 B1 plus A2 B2. So it will be given by A1 B1 plus A2 B2. Yes or no? And that dot product is 0 because A1 and A2 are A and B are mutually perpendicular. Yes or no? So if A and B are mutually perpendicular, I repeat, what we are reaching is A1 B1 plus A2 B2. A1 B1 plus A2 B2 is 0. Has anyone noticed something really beautiful and amazing here? X into X transpose, we have resumed, we have, gotten or received as an identity matrix. Sir, we are still absolutely clueless. Why are you doing this? Why are we doing this? Let me come back to what we started with. If you ever see a matrix, okay, in that matrix, if you see that here, if you multiply that matrix with itself, you get an identity matrix. If you ever see a matrix and if you multiply that matrix with its transpose, you get an identity matrix. Then, will I not say that, sir, if you are talking about that matrix technically contains vectors, which are unit vectors, and they are mutually perpendicular vectors. Did you understand this beautiful fact about orthogonality? Sir, are you not relating matrices with vectors? I am not. They are actually already related. So what do you mean by that? I am simply suggesting you of one very beautiful and interesting fact regarding matrices which can be related with vectors. What is that fact? Pay attention, everyone. If you ever see a matrix, let's say X, and if it is a 3 by 3 matrix, of course, it has elements like A1, A2, A3. It has elements like B1, B2, B3. It has elements like C1, C2, C3. And if somebody ever claims that this matrix X is an orthogonal matrix, if this matrix X is an orthogonal matrix, sir, what do you mean by orthogonal? Orthogonal here means that if you multiply this X with X transpose and if you get an identity matrix, then such matrix is called an orthogonal matrix. So the point here is, the beautiful fact here is that if you take or treat these vectors or these rows or columns as, vectors, for example, A1 I cap, A2 J cap, A3 K cap, B1 I cap, B2 K cap, B3 K cap, C1 I cap, C2 J cap, C3 K cap. These three vectors are going to be unit vectors and they are going to be mutually perpendicular. That means this dot this dot this, and this dot this will be 0. Not just that, this will be true column wise as well, which means if you have three vectors A1 I cap, B1 J cap, C2 K cap, A2 I cap, B2 J cap, C2 K cap, and A3 I cap, B3 J cap, C3 K cap, then also they'll be mutually perpendicular. That means this dot this dot this, and this dot this will be 0, and they'll be unit vectors. If you don't believe me, do it by yourself, you'll check. So did you understand this beautiful and interesting fact here? That if you ever see a matrix to be an orthogonal matrix, so in the world of vectors, this matrix represents unit vectors presented by rows or columns, whichever you wish to take, and they are mutually perpendicular. That's the beauty of an orthogonal matrix. Digest it, whatever I have said so far. Digest it. Let it get digested first. Then I'll proceed ahead or move further. So far, any confusions, students, tell me. Is there any confusion or doubt? Tell me. Everyone able to process this beautiful and interesting fact regarding orthogonality of matrices? So if two matrices are said to be orthogonal, what does it means in terms of vectors? A very interesting fact here. And on this, JEE Advanced asks you questions. This particular property. So you really don't have to do X into X transpose and I, and then you have to compare them. No. If you have cracked that it is orthogonal, that X into X transpose is I, you just treat the rows or columns as unit vectors and they are mutually perpendicular. If you apply this property, you'll reach to a lot of conclusions, a lot of beautiful conclusions. Shall I move ahead from here? If that part is very well understood by everyone. So with this, few more things come here. If we have cracked that, sir, A into A transpose is identity matrix. Yes, we have cracked it. That means I can take determinant on both sides. So if I know that A into A transpose is an identity matrix, so determinant of A into A transpose will also be an identity matrix. And determinant over the multiplication of matrices can be distributed, which means I can write it as A transpose as identity matrix determinant, and determinant of identity matrix is 1. Do you remember that? So here, A and A transpose, if you take its determinant, it will be A only. So this will be determinant A into determinant A, which is determinant A square. And determinant A square is 1, which means determinant of A will be plus minus 1. Another very beautiful and interesting fact regarding matrix or matrices. So what is that? That if you ever see an orthogonal matrix, then its determinant is going to be plus minus 1. Again, one more beautiful fact. You are going to remember that. But I did not say vice versa. I am not saying that if there exists a matrix whose determinant is plus 1 or minus 1, it will be orthogonal. No, I did not say that at all. Absolutely not. What I am saying here is that if you ever see a matrix whose determinant is if you ever see a matrix which when multiplied to its transpose gives you an identity matrix, it is an orthogonal matrix. And its determinant will be plus minus 1. Not just that, but something really beautiful and interesting. Have you all been able to digest this particular part? Yes or no? With this, if you have gotten this part clearly, I think let's move ahead. This is what we have discussed. Some examples they are trying to give you. For example, let's say there is a matrix A given to us. Always remember, if you ever see something like this, cos theta minus cos theta. And if you multiply this with A transpose, you will get it as identity matrix, which means, let's say in a question, let's say I'm given a matrix A, or let's say if I'm given a matrix X as any value you take, let's say cos 30, that's root 3 by 2. Sine 30, that's 1 by 2 degrees, I'm saying, right? Sine 30, that's 1 by 2. And cos 30 is again root 3 by 2, but with minus sign. Trust me, let's say if you ever see something like this, trust me, it looks like cos theta, sine theta, cos theta, sine theta minus cos theta. Trust me, without any hesitation, you can claim that this matrix, when multiplied with its transpose, will give me an identity matrix, which means row-wise, if you take, they are your unit matrix, and they are mutually perpendicular. Even if you see column-wise, they are unit matrix, and they are mutually perpendicular. Third conclusion, that determinant of this matrix, you can undoubtedly say, without even calculating, will be either plus 1 or minus 1. And if you calculate it, you can be more specific. Getting my point? I hope you're clearly seeing cos square theta minus sine square theta. So that is going to be minus 1. So being specific in this case, it will be minus 1. Everybody understanding this whole thing, yes or no? Everybody getting a crystal clear idea about this whole operation or thing we are doing. The same manner, one more orthogonal matrix exists in this manner. If you ever see cos theta minus sine theta cos theta, that also gives you an orthogonal. Why? You just do it by yourself. You multiply it with its transpose. You will receive an identity matrix. Check it out by yourself. Trust me, you will. Getting it, everyone? If you don't believe me, let me demonstrate it for this one A matrix, right? So there is this matrix A, C minus S, S, C, right? We have C minus S, S, and C. Cos theta and sin theta, I am writing in this short format. So let's say this is X. So what will be X transpose? X transpose means rows and columns interchanged. So this will be C and minus S like this, and S and C like this. So if I do X, X, T, which means if I multiply this matrix X with its transpose, so it will be given by rows from here, columns from here. So C, that's C square, minus S, that's plus S square. Then CS, that is CS, minus SC is minus CS or SC. Then SC with the CS, SC minus SC, yes or no? Then SC with SC is S square plus C square. Do I really need to teach you that cos square theta plus sin square theta is 1? This minus this is 0. Sin theta, cos theta, sin theta, cos theta is 0. And sin square theta plus cos square theta is 1. That's clearly nothing but an identity matrix. It's clear a proof here. Yes or no, all the participants? Everybody got this? Everybody understood the whole concept of orthogonal matrices? With this, we'll move ahead with idempotent and involutory matrices as well. But let's take a 10 minutes break and then we'll resume. So it's 11:30. We'll resume at 11:40. Is it fine? So you also hydrate yourself, stretch, and then we'll resume at 11:40 or maybe 45. Let me just take a break. Right? Is that okay? So we'll resume in 10 to 15 minutes. Hydrate yourself, take a break, stretch yourself, go for a little walk, but stay around, and then we'll come back. Definitely. Thank you so much. Okay, come back everyone if you can hear my voice, if you can hear me, if you can see me, if you are roaming around, the voice is clearly still audible, then come back. We are resuming. We are getting started with this again discussion. So, everyone, you can hear me. I hope you can see me. If you can hear my voice, come back, everyone, come back. I hope you have hydrated yourself, stretched yourself, went for a walk. Then, if the system is still open, I'm clearly visible and audible, then if you can hear my voice, then come back, sit at the desk and start watching it again. We are resuming our discussion on matrices. So the entire chapter matrices is going to get covered. Theoretically, yes. Conceptually, yes. With a lot of complete concepts thoroughly and comprehensively, we'll be doing here. Along with this, yes, we are doing some decent amount of questions to consolidate those concepts, those learnings. Absolutely, yes. But this is sufficient? Absolutely not. Sir, then what are we supposed to do? Solve PYQs, solve mains and advanced PYQs. That will help. That will definitely help. So here we are. What does it say? The first part, idempotent matrix. Sir, what does it mean? A square matrix. When it is multiplied with itself, if it generates the original matrix again, then are you not realizing something clear and straightforward? That sir, if a matrix when multiplied with itself gave you A, so what will be A cube? Sir, A cube will be A square into A. What is A square? That's A, so it is A into A. That's A square, so that is again A. I hope in the same fashion you can prove all the higher powers A to the power 4, A to the power 5, A to the power 6 and so on all to be A. Are you learning something really interesting here at this stage? I am saying that if you ever in a question are able to check or prove that there is an idempotent matrix where A square is A, that concludes that all the higher powers A cube, A to the power 4 and so on will be A. Yes or no? And if I have cracked it, that if I could see that A square is A and I'm able to conclude that A cube, A to the power 4 and all the higher powers of A are A, then let's say if I'm asked, what is A to the power 2025? What is A to the power 2025? Yes or no? So I hope you are clearly noticing that sir, A to the power 2025 is not what? A. So I hope it's a really simple task. But sir, how is it going to be really helpful or beneficial? I'll come back to that part where somebody in the beginning was asking me, sir, can you teach us how to deal with higher powers of a matrix? Let's talk about that part. Let's say there is a matrix B, which I could split into A plus I, where I am clearly seeing that A here is the idempotent matrix, where I is your identity matrix undoubtedly. And let's say here in this case, I am told to find, sir, what is going to be B to the power? Let's say what is going to be B to the power? Let's say 2026. What is going to be this? So what I'll say is that, sir, B to the power 2026, I could have written as what? I could have written this as A plus I or I plus A to the power 2026, yes or no? Now with this, if I expand it with binomial expansion, do you remember that? So binomial expansion here says that you will write it as, it's like 1 plus x to the power n, nc0, x to the power 0, nc1, x to the power 1, nc1, nc2, x to the power 2, and so on. So that whole idea if I do here, 2026, c0, a to the power 0. So it is identity matrix, and this c0 will be 1. So it is I plus. The next thing will be 2026, c1, a to the power 1. The next thing will be 2026, c2, a square. The next thing will be 2026 c3 a cube and so on until what? Until the last term, which will be 2026 c 2026 a to the power 2026. Everybody getting that conclusion, yes or no? But sir, why are we really doing this? Have patience. Have patience. One of the best skills you can master in your life is learn to be patient. Patient means not that doctor kind of patient. Patient means to have that attribute of being a patient guy, a patient person. So here, if I Try and simplify this result. Which result, sir? This result. I hope you remember this whole thing where we are writing it as 1 plus a to the power 2026, yes or no? Which is eventually nothing but what? B to the power 2026. So there I'm telling you that we know A is an idempotent matrix, which means A square, A cube, and all the higher powers of A are A. So there can I not write this as I plus 2026 C1 A plus 2026 C2 A plus 2026 C3 A, because A square, A cube, all higher powers of A are A. And this goes on till the last term 2026 C, 2026 A, and that power again results into A. Getting it? And this all we are writing as B to the power 2026. Now the most beautiful thing which I'm constantly trying to tell you is this result. Sir, which result? Have patience. Just learn, watch, and see. Pay attention. Sir, this I stays outside. It doesn't matter much here at this stage, but this part. If I take A common, if I take this A common, so of course it's matrix versus a scalar. So matrix I'm keeping common, multiplied with this scalar. This scalar is 2026 C1 plus 2026 C2 and so on until 2026 C 2026. Sir, it has a certain problem. What problem? Do you remember something which you must have studied in binomial only, that NC0 plus NC1 plus NC2 until NCN? Do you remember that number of subsets 2 to the power n? Remember that formula, yes or no? So if I could ask you to use that formula here, sir, it has something missing in it. 2026 C0. Had that term been also be there, it could have been written as 2 to the power 2026. So if I add that term and subtract that term, it will be balanced. So this whole thing, can I not write? This whole thing, can I not write as 2 to the power 2026 minus, this was missing. What was missing? 2026 C0. And 2026 C0 is nothing but what? It is clearly 1. Everybody got that? And if you have gotten that, you have gotten that result. Which result are we talking about? So the result where we are mentioning or saying that we were supposed to crack B to the power 2026. So there, I think you have B to the power 2026. How? Let's talk about that now. I think some of you must have gotten it already now. So sir, we were supposed to crack B to the power 2026, which is going to be I. So I we know. A we have already cracked, because B we have split it as A plus I. B we have split it as A plus I. So I we know, A we know, because we had B. So if we have I, if we have A, that's a scalar, which is basically nothing but 2 to 6 minus 1 times A. So if we have I, if we have A, if we have this scalar getting multiplied to this A, and when I is added, will you not be able to generate your final answer B to the power 2026? So those who are asking in the beginning, that sir, how do we deal with the higher power of matrices? Are you realizing it now? That there are methods, there are ways, there are techniques, but those techniques become handy when you know the types of matrices. For example, idempotent. Now, one more thing is very interesting here, that idempotent matrix will always have its determinant as either 0 or 1. Sir, why are you saying this? I am saying it because we know math. We know that A square is A, even A cube, A to the power 4, all these higher powers of A will be A, indeed. So there we know that determinant can be taken on both sides. So it will be determinant of A square is equals to determinant of A, because determinant of A square or square of determinant of A is same. Power and determinant can be interchanged. With this, I hope I can write it as determinant of A square minus determinant of A to be 0, because it's not a matrix anymore, it's a value. Determinant of A scalar quantity can be taken common, so determinant of A times determinant of A minus 1 to be 0, and if it is 0, so either determinant of A is 0 or 1. That's all what I'm saying. You know it, right? X square is X, then X is either 0 or 1. Everybody knows that. Everybody. Give me a quick update. So have you gotten a decent clarity on a matrix being idempotent? Yes or no? Now, pay attention everyone. Pay attention everyone. Now the next part. Involutory matrix. Now what is an involutory matrix? There is a square matrix, And if it is squared and gives you an identity matrix, then such matrix is said to be an involutory matrix. Again, those who are asking about, sir, how do we deal with higher powers of matrix? Let's say there is a matrix B, which I could write as A plus I. Again, there is a matrix B, which I could represent as A plus I. And now I am asked B to the power, let's say 200. But I can write it as A plus I to the power 200. Now again, by binomial expansion, I can write it with a lot of ease. But let's say by performing some operations on A, that means A square I did, A cube I did, and ultimately I started noticing that it is I. So the moment I crack A square is I, what will be A cube? Sir, A cube will be, I hope you are noticing, A into I, because it is going to be what? I hope you are noticing A square if it is I. I repeat what we have just noticed, that A is an involutory matrix, so A square is I. So if A square is I hope you are clearly noticing A cube will be what? A square into A. That is going to be what? I into A, that's A. What is A to the power 4? A to the power 4 is again going to be what? A square into A square. So A square is I. I hope you are noticing. So that's again I into I. So that's how you will again see a pattern. And once you see a pattern, again you can generalize it and you can work it out with a lot of ease. I am not giving you a lot of questions, but I'm giving you the general cases that if you could crack that by multiplying A with it itself, I could find it to be an identity matrix. And if I could find that A square is I, which means I could crack that A is an involutory matrix, I'll again use this property here and I will try and conclude it like this. Getting it, everyone? Yes or no? Now, again, the whole idea is really simple. If somebody says A square is I, determinant of A square will be determinant of I. Determinant of I means what? Identity matrix. Its determinant is 1. So if A square is 1, determinant of A will be plus minus 1. So whenever somebody says that there is a matrix which is involutory matrix, its determinant is going to be plus 1 or minus 1. Comfortably getting it? Everyone, all the participants, yes or no? Any confusion so far? I hope this whole thing which we have learnt is very well understood by everyone. Nilpotent, that's again a very interesting, very interesting. And you will see most of the questions are framed around a nilpotent matrix. What does it mean? Again, I'll take an example first so that I can make you understand this whole scenario. Let's say I'm given a matrix B and it's any higher power. Let's say 101 is what we are asked, right? And again, I could split B into two matrices I and A, sum of I and A. So technically, I'm trying to find I plus A to the power 101. Now, by observing A, I notice that A to the power 1 is A square is A cube is A. Sorry, A square is something, let's say as A square, A cube is something as A cube. But when I multiplied it again, I found it to be null matrix, which means A to the power 4 was null. So will I not say A to the power 5 will be A to the power 4 into A, which is again null into A. So I hope now I can say that all the higher powers from now on will be null. So what is the advantage? The advantage is absolutely simple again. I plus A to the power 101, I'll be writing as what? I, that is what? I hope you're clearly noticing that it will be what? 101 C0 A to the power 0, which is I. So this is 1 into I, which is I, plus 101 C1 A to the power 1 plus 101 C2 A square plus 101 C3 A cube plus 101 C4 A to the power 4 and so on until 101 C101 A to the power 101. Now, everybody, please pay attention. Now, what happens here in this category of questions is when you are dealing with higher powers of B, where B could be splitted as I plus A, where A was found to be a null, A to the power 4 was found to be a null matrix, which means we could claim that A is a nilpotent matrix. There, something very magical is going to happen, that A to the power 4 onwards, all of these terms will start becoming null. Null into anything, null into anything. So null plus null plus null plus null. All of these will be added as null. So they all will not contribute because this is null, O. So null plus anything will be that anything. So ultimately this whole problem boils down to as I plus 10C1 is 101, that's A, plus this is 101 C2, that's A square. Then it is 101 C3, A cube, and that's it. That's your answer. So that's your b to the power 101. So when you were asked to deal with a higher power of b, which is as used as 101, you really don't have to multiply b 101 times. You really don't have to look for a pattern. But what you clearly saw was that b could be expressed as I plus a to the power 101. There I could apply binomial. I could see a pattern in A which started becoming null, which means A was a nilpotent matrix, and that's how I could restricted it to these four terms. And these four terms we can very easily predict. And such questions are constantly asked by JEE mains and advanced in these recent years. And that's why I'm giving you this pattern, this strategy, this technique, this method. Everyone comfortably getting this? Yes or no? All the participants. One more thing you should pay attention to is that here, if I'm saying that this is a nilpotent matrix, then of course there exists a positive integer m such that a to the power m is null, that is 0. In the previous example, a to the power 4 was null. So there m was 4. So this m is the least positive integer for which it happened. And this m in our example or case is called the index of that nilpotent matrix. Yes or no? Yes or no, everyone? Everyone got that? Everyone understood this whole idea comfortably? Now, there comes another concept, a beautiful concept towards which we are moving is said to be the adjoint or adjugate matrix. What is it? Let's start talking about that. Pay attention, everyone. We are now moving towards the part which is considered to be the climax or the conclusion of this chapter. So adjoint, inverse, matrix, polynomial, Cayley-Hamilton, and all that we'll be discussing now. And with this, we'll be reaching towards the culmination of this chapter. So far, we were learning and expanding. Now we'll be narrowing it down. Yes or no? So with this, pay attention, everyone. The next thing which we'll be exploring here is this one. Let's say there is a matrix A. So for this matrix A, the entries are like 2, 3, 4, and let's say 1. Can you help me with finding its minor? So if I wish to write minors of elements of this A respectively, so what will I do? Sir, for writing the minor of 2, remove the row in column which 2 contains and just write that element. For 2, it will be 1. For 3, the minor of 3 will be 4. For 4, the minor of 4 will be 3. And for 1, the minor will be 2. I hope it's absolutely understandable without any confusion. So that's the minor. But with minor, if I introduce the sign scheme, I'll start getting cofactor. So what is going to be the cofactor here? So cofactor of A is going to be, I'll introduce the sign scheme. So this element is positioned at 1, 1. First row, first column. 1 plus 1 is 2, which is even. So for even, you use plus sign. This 4 is positioned at second row, first column. I hope you're paying attention, everyone. Yes or no? So this 4 is positioned at, first row, second column, 1, 2. So 1 plus 2 is 3. 3 is odd. Odd means you put a negative sign. Again, when you look at this 3, this is positioned at second row, first column, 2, 1. 2 plus 1 is 3. 3 is odd. So for odd, you put a negative sign. Sign scheme, when you follow, you start writing cofactors. So previously, they were just minors. When I introduced sign, they started becoming cofactor. This particular part 2, this is second row, second column. 2 plus 2 is 4. 4 is even. So with even, you use a positive sign. That's how you found the cofactor. Now, if you have found the cofactor, you just do one thing. Which thing, sir? You write the transpose of the cofactor of A. If you do that, what do we get? So transpose means what? Rows and columns are interchanged. Rows and columns are interchanged. So there, 1 and minus 4 become your first column, and minus 3 and 2 become your second column. This thing here, 1 minus 3 minus 4, 2, is nothing but actually the adjoint of this matrix A. Sir, why are we really doing all this? Why are we having a matrix? Then why are we finding its minor? Then why are we finding its cofactor? And then why are we taking its transpose? Have patience. I'm going to explain it very soon. The beauty of adjoint of a matrix is this, that if now you multiply this matrix with its adjoint now, if you multiply this matrix with its adjoint now. First of all, are you noticing that adjoint? What is this giving to you? Sir, if I forget all of this, if I just tell you something really interesting here. Sir, if there is a matrix which has elements A11, A12, A21, A22, that's our matrix, let's say for a while, X. Now, I hope you're understanding it's minor in cofactor. So it's cofactor if I write. It's cofactor if I write. Its cofactor will be given by what? Cofactor of X I'm writing. So cofactor of X I'm writing as cofactor of A11 I'm writing as C11. Cofactor of A12 I'm writing as C12. Cofactor of A21 I'm taking as C21. Cofactor of A22 I'm taking as C22. Paying attention everyone. Now if I take its transpose, if I now take its transpose. So transpose of cofactor of A. So cofactor of X, and I'm taking its transpose now. So transpose will look like what? C11, C12 becoming the first column, C21 and C22 becoming the second column. Sir, why are we really doing it? Have patience. So I'm going to explain it now. I am asking you to multiply. What is it? Sir, in our language, we have started calling it adjoint of X. So I'm just asking you to multiply this X with its adjoint. Okay, let's try and do it. So X when multiplied with adjoint of X. Sir, what do we get? Okay, let's talk about it. So rows I'll choose from here. Columns I'll choose from here. You know that matrix multiplication. So A11, C11. So I'll get A11, C11 plus A12, C12. So this will be A12, C12. Do you remember something interesting we have discussed? Sir, what is that interesting thing? Any rows element multiplied to their corresponding cofactors give you what? The value of that determinant, the determinant of that matrix. Remember that? I hope you are getting it. A11, A12 with C21, C22. So A11, C21 plus A12, C22. So elements of any row multiplied with the cofactors of some other row give you the value as 0. Remember that property, yes or no? Similarly here, A11, now, what I'll do is second row I'll take, first column I'll take. So A21, A22 with C11, C12. So it will be A21, C11 plus A22, C12, this row with this column. Again, elements of any row getting multiplied with the cofactors of some other row will give you the value as 0. Remember that property, which we have discussed when we were talking about determinants. So in the previous one shot of determinants, we did cover this particular property. Now the third, A21, A22 with C21, C22. So A21 with C21 plus A22 with this C22. Everybody noticing that result? Yes or no? Sir, what have we attained by doing this? Pay attention everyone. You are very close to result, a very important result, which will lay the foundation of almost all the upcoming properties we are going to study related to adjoint and inverse. What is that? Let's have a discussion on that. So all I'm saying now is a very beautiful and interesting property here. What is that property? Please check it out. Here, X into adjoint of X, X into adjoint of X, I am receiving as A11, C11, A12, C12. That's clearly the determinant of matrix X. So this here contains determinant of this matrix A. A11, C21, A12, C22. If elements of any row are multiplied with corresponding some other rows cofactors, that gives you the value 0. This is what we have discussed when we were discussing the properties of determinants. Remember that last session? One shot of determinants. A21, C11, A22, C12. So corresponding rows multiplied with some other rows cofactors give you the value 0 here. And this is A21, its cofactor. A22, its cofactor. When it is done, it gives you the determinant of that matrix. If I want, I can take determinant X common. So if I'm taking determinant X common, that's a scalar taken common. So it is left with 1, 0, 0, 1. And 1, 0, 0, 1 is nothing but an identity matrix. That's the beauty here. What are you saying, sir? We are still clueless. I am saying that a matrix, when multiplied to adjoint of its matrix, gave you determinant of that matrix times identity matrix of that order. Let's say the order was 2 here. So it is I2, identity matrix of order 2. If we could reach to this conclusion, trust me, it leaves you with something really beautiful, interesting, and as a property, it gives you something really amazing. What do you mean by that? If I divide both the sides by determinant of x, so x into adjoint of x divided by determinant of x is identity matrix. Sir, what are we still doing? We are absolutely clueless. Let's say for a while, say that adjoint of x upon determinant of x is a matrix y, because adjoint of x will be a matrix. 1 by determinant x is a scalar. So adjoint of x when divided by 1 by determinant of x will still be a matrix, and that matrix I'm denoting y. So this particular part can be written as determinant of x into determinant of y is equal to as identity matrix. Now this gives you something really beautiful and interesting here. What is that interesting thing? That interesting thing says here that there exists a matrix A, which when multiplied with the matrix y is giving you an identity matrix. The beautiful thing here is that for x, if there exists a matrix y, by multiplying which, if I'm able to generate a matrix I, this matrix y in the world of matrices is said to be the inverse of matrix A. In the world of numbers, what happens is if there is 2 and if you multiply 2 by 1 by 2, you get 1. So 2 and 1 by 2 are reciprocal of each other. The same concept of reciprocal in the world of matrices is treated as the concept of inverse, which means there exists a matrix X, which when multiplied with Y gave you an identity matrix. So this Y here is called the inverse of X, which means you can say Y is equals to X inverse. This is not X to the power minus 1, which is not 1 by X matrices reciprocal you don't take. This is X inverse. And what was Y actually? Sir, Y was this. So technically we are defining the inverse of a matrix as adjoint of that matrix divided by determinant of that matrix. Did you get this beautiful property? Did you all understand this? Or shall I re-explain this? All the participants, be quick and tell me, have you all been able to process this whole idea? So if I get back to the discussion of adjoint of a matrix, did you get it? And if I now get back to this discussion, I hope it makes complete sense that we were given a matrix, we found its adjoint, and with this, what we see now is that if this matrix is multiplied with its adjoint, I'll get determinant of this matrix into an identity matrix for sure, because we know this property, right? But for a 2 by 2, you can find its adjoint by using a short technique. What is that short technique? Let's try and learn that. That short technique here says that if you ever see 2, 3, 4, and 1, and you want to write its adjoint, then always remember, first of all, this principal diagonal elements, leading diagonal elements, just swap them. So if it was 2, 1, just write it as 1, 2, just swap them. Second thing what you do is, these non-principal diagonal elements, just keep them there only, but just put a negative sign before them. What are you trying to say here is simply this idea that let's say there is a matrix B, which is given by A, B, C, D. This short trick is valid for a 2 by 2 matrix only. And I want to write its adjoint. Then the short technique says, interchange the principal diagonal elements. That means this A and D, interchange them. And before this B and C, just put a negative sign. Just put a negative sign. Trust me, this is how you write the adjoint very quickly for a 2 by 2. Everybody understood that whole idea? Everybody got this whole thing? Yes or no? All the participants. So are you all getting comfortably the concept of adjoint? So if I'm ever asked to find the adjoint, what I'll do is, if I'm ever asked to find the adjoint, what I'll do is, for a 3 by 3, I'll have to manually find the minor. Then from minor, I'll define cofactors. From cofactors, I'll take its transpose. And once I've taken the transpose, this process finally gives me an output. That output is called the adjoint. Although minor and cofactor you do at once, you don't have to perform 2 double steps like minor and then finding cofactor. You can find the cofactor directly. Minor with sign scheme followed are cofactors. And when you take its transpose, adjoint. If you are still confused with the concept of adjoint, let me help you the concept of adjoint with a question. Shall we take a question? This here is a very beautiful question. So let's try and find adjoint of this matrix A. Shall we? Paying attention, everyone. So first of all, let me write minor. I'll do it step by step so that you stay clear. So minor of A, if I wish to write, I hope you are comfortably getting how am I going to do it and what am I going to do now. Minor of A, if I wish to find, how will I do it? Sir, for 1, I'll remove this row and this column. So I'm left with 1 into 3, 2 into minus 3. So 1 into 3 is 3. This is minus 6, which is plus 6, right? Plus, minus. So 3 minus minus 6, that's plus 6. 3 plus 6 is 9. So minor of 1 will be 9. Everybody got this? Now, for this one, if I want to find the minor, I'll remove this row in this column. So 2 into 3 is 6. Minus 1 minus 3 is 3, which is again minus. So 6 minus 3 is 3. So this element will be written as 3. Getting it, everyone? Now, I'll remove this row and this column to find the minor of this one. So it will be 4 plus 1. I hope you are noticing it. So 4 plus 1, that's 5. So the element here will be plus 5. Getting it, everyone? Now, if I want to find the minor here for this 2, it will be 3 minus 2. So 3 minus 2 is clearly 1. Now, if I wish to find the minor of this one, so it will be 3 plus 1, which is 4. Now, if I wish to find the minor of this 3, so it will be 2 plus 1, that's 3. I hope you're able to process it. If I wish to find the minor of this minus 1, it will be minus 3 minus 1, that's minus 4. If I wish to find the minor of this 2, so it will be minus 3 minus 2, which is what? Minus 5. And if I wish to find the minor of this 3, it will be 1 minus 2, which is again minus 1. Did you all understand this part comfortably? All the participants, yes or no? But I have still not been able to write the cofactors. I am still at this stage of writing the minors. Now, if I wish to write the cofactors, how do I introduce cofactors? So in order to introduce cofactors, I'll use the sign scheme. I hope for a 3 by 3, the sign scheme follows a pattern. The pattern is plus minus plus, minus plus minus, plus minus plus. Remember it. Remember it. It always works. So plus minus plus, minus plus minus, plus minus plus. That's how you are done with the cofactor part. Sir, but cofactor, is it enough? Is it sufficient? Absolutely not. Once you have written down the cofactors, take its transpose. Take its transpose. So transpose means 9 minus 3, 5 is becoming our first column. Minus 1, 4 minus 3 is becoming our second column. Minus 4, 5 minus 1 is becoming our third column. So this thing here, which is the adjoint, I'm saying, because this is the transpose of your cofactor. So this here is said to be the adjoint of A. Did you get it beautifully? Did you all understand this? What did I do? 3 things. I gave the minor. With minor, I followed the sign scheme. I gave the cofactor. And with cofactor, we took its transpose. Ultimately, we reached to the adjoint. Yes, all the participants. Now with this, one more thing here. Shall I stretch it a little to one more concept? What is that concept? Look at this part. The concept here says that, let's say, if I am, instead of adjoint, let's say asked to find the inverse of this matrix. Let's say we are not asked to find the adjoint, we are asked to find the inverse. So inverse, how do we find? I hope we are at the adjoint of A. If I find determinant of A, so if I find determinant of A, how do we find determinant of A? This is 1, 1, 1. Although you can find determinant of A with the simplest idea. So what is that simplest idea? You have cofactor of A, yes or no? So if I choose any row, I know that trick. If I choose any row, let's say I have chosen this row, or why not choose the first row? So if I choose any row and multiply that row with its corresponding cofactors. By the way, you tell your tricks. I'll be really happy if you could tell us or share your insight. So if I choose any row, let's say 1, 1, and 1. And if I multiply that row with its corresponding cofactors, I think I'll be able to find the determinant A here. Yes or no? We need to find the inverse here. So I repeat, I have chosen a row 1, 1, 1. The cofactors of 1, 1, 1 corresponding 1, 1, 1, the cofactors of them, if I multiplied them to these elements and if I add them up, I'll get the value of the determinant, yes or no. So for 1, 1, 1, I think cofactor was 9 minus 3 and 5, because this is the adjoint. If you don't believe me, we got 9 minus 3 and 5. So 9 minus 3 and 5, if I introduce 9 minus 3 and 5, this here will give me the determinant of A. So what is the determinant of A? Determinant of A will be 9 minus 3 and 5. 5 minus 3 is what? 2. 9 plus 2 is 11. So determinant of A we receive as 11. Sir, what is the idea or whole point of this? I hope some of you must have remembered this whole thing, which I'm doing right now is this, that if I have determinant of A, if I have adjoint of A, determinant of A we have found as 11. So I hope you remember, if I ever wish to define A inverse, so we have just learnt a formula, A inverse is given by adjoint of A upon determinant of A. Which means if this is adjoint of A and if I divide it by 11, that means if I multiply it by 1 by 11, that's A inverse. So what are you trying to say? I am trying to give you a very simple, straightforward idea or hint or logic that if you multiply A with A inverse, this is your matrix A and this is your matrix A inverse. If you do the matrix multiplication, I bet you, I tell you with complete conviction, 100% assurance, you are going to get A inverse into A as I identity matrix. So when you multiply this A with A inverse, you'll get I identity matrix. Did you get my point? So ultimately, if you check it by yourself, you can do it. A into A inverse is going to be received as identity matrix. So first of all, that's the concept of inverse of a matrix. Inverse of a matrix means inverse, if you have found of a matrix, then that matrix, which is the inverse, multiplied with that original matrix, will always give you an identity matrix. Everybody got that whole conclusion? Everybody comfortable with this whole idea of inverse of a matrix? How do we find it? Yes or no? So there are certain properties related to adjoint, most of which we have just learned. This one I have already explained you, that if a matrix is multiplied with its adjoint, or adjoint of a matrix, if it is multiplied with the matrix, it always gives you the determinant of that matrix into identity matrix. We have just learned this property. We have seen the proof of this property and it is right there in front of you. I hope nobody is going to forget it, because IIT JEE is in madly love with this property and they'll ask you questions based on this, directly or indirectly, very subtly. Now there comes one more property. I'm not giving you this proof because had it been the whole class, I think I would have done it. But here it is the one shot. I'm just giving you the property. It says adjoint of A's determinant is determinant of A to the power n minus 1. What does it say? Let's say if I go back to this question and if I ask you that can you find determinant of adjoint of A, then you really don't have to find the determinant of adjoint. This thing was adjoint. I hope you remember that. You really don't have to do it. You could have simply said, sir, it will be equal to determinant of A to the power n minus 1. N is your degree, which is 3 minus 1. The determinant of A, we have found it as 11. 11 to the power 3 minus 1 is 2. So your answer would have been 121, which means, let's say if you are asked to find out its determinant, you really don't have to find out its determinant if you know the determinant of A. I repeat, always remember it as a fact, as a property, that determinant of adjoint of A is always determinant of A to the power n minus 1, where n is the order. So what happens for a 2 by 2? I hope you are clearly learning it and you are understanding it. Let's say there is a 2 by 2. Let's say there is a 2 by 2. For 2 by 2, determinant of adjoint of, let's say, x. X is a 2 by 2. So it will be determinant of x to the power n minus 1, which is 2 minus 1. So it is determinant of x. So for a 2 by 2 matrix, its determinant and determinant of its adjoint is going to be same. Will you all remember that? All the participants. Getting it or not? Everyone. Understanding this? Shall I move ahead from here? The next property. It's again a very beautiful one, where it says that let's say you're dealing with adjoint of A. Then trust me, you really don't have to calculate it. It will be determinant of A to the power n minus 20. So what does it mean? Let me try and help you out here. With this question only, shall I help you? I think this I'm bringing here. Just give me a moment. I am bringing it here so that it can be explained very easily. Just give me a moment, all the parts. This is adjoint of A, right? Now let's say, now somebody asks you to find out adjoint of A. Now the beautiful thing here is that adjoint of A somebody is asking you to prove. Just give me a moment. Let me just remove this. I repeat, all I'm saying is hold on for a while, students. Give me a moment, everyone. All I'm giving you is a very simple conclusion. Adjoint of A. Now this property says that adjoint of A. I mean, first you find adjoint of A. Once you have found adjoint of A, then again you find its adjoint. Is it not going to be a very cumbersome process? Absolutely not. If you know this property that it is determinant e to the power n minus 2 times A, matrix A, which means here, for this question, which question here? For this question, let's say I am asked to find out adjoint of A. Then you really don't have to find adjoint of A. What you need to do here is, it is given by this particular property which says determinant of A to the power n minus 2 times matrix A, which means determinant of A to the power n minus 2. N is the order, so it will be 3 minus 2 times the matrix A. Which means what? I hope you are clearly noticing that 3 minus 2 is 1, determinant A was 11, so 11 times the matrix A. And matrix A was already there, 1, 1, 1, 2, 1 minus 3, minus 1, 2, 3. Isn't it really beautiful and interesting? What does it mean? If I could simply multiply all the entries by 11, I will be getting a matrix. And that matrix is going to be adjoint of A. Can you believe this? It is such a short method. So you really don't have to find adjoint of A. Then again, it's adjoint. You really don't have to process it twice. Absolutely not. If you are given a matrix A, you just find its determinant. Apply this property, determinant A to the power n minus 2, into that original matrix, and it will give you adjoint of A. I hope you got my point. Is it not absolutely simple and understandable? Everybody getting this particular property, comfortable with this? Now, the way we were dealing with transpose, in the same fashion, we deal with adjoint as well when product is being done. What does it mean? Let's say you are asked to multiply 3 matrices, and then you are asked to take the adjoint of their product. So reversal law says here, the same which we were doing with transpose, that when transpose was taken, Z transpose into Y transpose into X transpose, the same we do with adjoint. So here also I can write it as adjoint of Z times adjoint of Y times adjoint of X, but the order reverses, the order changes. Yes, I'll be discussing those properties as well. Don't worry, I'll come to all those properties. Don't worry. But thank you so much for highlighting these. I'll cover all of these. Absolutely. So with this, I hope you are clearly noticing this part. With this, remember one more property. If at this stage we are about to discuss it, why should we not? X into Y into Z, it's inverse. So what you're saying is multiply these 3 matrices and then find their inverse. This also follows the reversal law. Z inverse into Y inverse into X inverse. So the way we are doing the reversal law with transpose, the same follows for adjoint, the same follows for inverse, and the root cause is simple because transpose was doing it and adjoint uses the transpose internally. So it must be done with adjoint and inverse as well. I'm not giving you the proof, but I'm telling you the logic. And I hope that is very well understood by everyone. Yes or no? Everyone, yes or no? So that part I hope makes complete sense. And this beautiful property, the way we learned that transpose and powers can be interchanged, transpose and inverse can also be interchanged. I repeat, what have we just learned is that, sir, we know that if determinant A to the power 5, when its determinant is needed to be taken. So you said determinant of A you take and then 5 you raise it to. Or what we learned was that determinant A to the power 10 and then you take its transpose, or you take its transpose and then you raise it to the power 10. It is also same. Similarly, there exists one more property that you are finding inverse of a matrix and you are raising it to power 10. Then you can raise it to power 10 and then you find its inverse. Both are same. Which extends towards one more property, which gets extended towards one more property, that this one, where you are taking transpose of inverse or inverse of transpose, it is same, which means you are taking transpose of a matrix and then you are finding its inverse, or you found its inverse first and then you take its transpose. They can be swapped, they can be interchanged. Shall I repeat that? The whole thing. Have you gotten it clearly? Everybody, all the participants. Shall I move ahead from here, all the participants? So now, there I'm going to talk about few more properties. Which properties? I think this has been covered. I have just covered it. This property is also self-explanatory. This -1 can be distributed. So k to the power minus is like reciprocal of k, A inverse is A inverse. This is a very beautiful property on which JEE Advanced has asked a question this year. In 2026, Advanced has asked a question on it. So what does this property say? This property here says that adjoint of A inverse is A upon determinant of A. Why does it exist? Let's talk about that. We know that any matrix, when multiplied to its adjoint, always gives you determinant of A into the identity matrix. So if I multiply both these sides by determinant of A, can I not write A upon determinant of A into adjoint of A as identity matrix? So previously we were saying that inverse of A is adjoint of A upon determinant of A. Can I not see in this context beautifully that adjoint of A when multiplied with A upon determinant of A is giving you an identity matrix? So this and this are inverse of each other because product of these two matrices is the identity. So they are inverse of each other. So will I not say that adjoint of A, if I wish to take its inverse, it will be given by A upon determinant of A? Everybody able to process this whole idea? Everybody able to get this? Or shall I re-explain this? This is that part of this chapter where things start becoming a little difficult, but I hope these properties, if seen well, understood well, can make a lot of sense here at this stage. Getting it or not, everyone, all the participants? Shall I move ahead from here? Getting it, everyone? So with this, that's exactly what we are given over here, I think so. Adjoint of A inverse is A upon determinant of A. That's exactly what we are told. No problem regarding this. I hope this you write as adjoint of A whole inverse, or this you write as adjoint of A inverse. It is same. They are same. They both are same, exactly same. With this, something really crucial, insightful and interesting, if I could tell you with an example. Let's say there is a matrix A which is given by 3, 0, 0, 0, 5, 0, 0, 0, 2. This is a diagonal matrix. This is a diagonal matrix. So for this diagonal matrix, let's say if I wish to write its inverse, always remember the short trick. Its determinant is non-zero. 3 into 5 into 2, that's clearly 30, non-zero. So it is an invertible matrix. It's non-singular. Its inverse can be found. So if its inverse can be found, there I'll say that A inverse is always given by that same diagonal matrix, but its diagonal entries reciprocal is taken. So reciprocal of 3 is 1 by 3. Reciprocal of 5 is 1 by 5. And reciprocal of 2 is 1 by 2. Other entries you keep as 0, 0. And that's how you can directly write the inverse of a diagonal matrix. Trust me, when you multiply this matrix with this matrix, you are going to get an identity matrix. Why? Because we know diagonal matrix into diagonal matrix is simply a product of their diagonal entries. So 3 into 1 by 3, 1. 5 into 1 by 5, 1. 2 into 1 by 2, 1. Other entries will remain 0. Getting it, everyone? I hope no confusion on this. So will you remember these properties? One more property which left untouched was technically based on this property, actually based on this particular property. Let me just see it. This one. It was an extension of this property. Let me try and teach you this here. I'll tell you the whole property. Adjoint of, and so on. A lot many times adjoint is appearing of adjoint of A. So a lot of brackets are also there. And then its determinant is needed to be taken. There, if I'm told, this adjoint is appearing m times. This adjoint is appearing m times. Then what does this property say? Can somebody write in the comments this beautiful property? I think somebody has already. There is one thing which is missing there in that suggestion which is given in the comments. Can somebody give me the correct version of it? What did I do? There is a matrix A, which is of course an n-ordered square matrix. So this is a matrix A, which is having order n, where I'm asking you to find the determinant of adjoint of A, where adjoint has appeared m times. Then do you remember this property? A very important, a very crucial, a very phenomenal, amazing property on which JEE is in a short manner going to ask a question in every single shift. This is that important and crucial property. Can somebody help me with this property? Anyone in the chats. I'll be really happy if you could. Anyone, be quick. Yes, it's late, but I'm sure some of you are watching it sincerely and could answer this one. I hope most of you must be able to recall it. It is always given by determinant of A to the power n minus 1 to the power m. The mistake, absolutely Yashwant, I'm glad you told it. N minus 1 to the power m, it's not n, m times, so it's n. One thing which you all must notice is a very beautiful fact here, that it is not a to the power n minus 1 whole raised to the power m. No. This power m is the power of n minus 1. The whole difference is this, that let's say if I ever write 3 to the power 5 whole raised to the power 6, and if I ever write 3 to the power 5 raised to the power 6. So they are not same. Because here it is a to the power m whole raised to the power n. So this is 3 to the power 5 into 6. That's 30. Yes or no? So this is 3 to the power 30. But here it is 5 to the power 6. That means 5 into 5 into 5 into 5. Yes or no? So that's different. This is 3 to the power 5 to the power 6. Can somebody help me with 5 to the power 6? This is 125 into 125. What is 125 into 125? Let me quickly do it so that I can give you the exact figure. Hold on for a while. 125 into 125. That is 15,625. So this is actually 3 to the power 15,625. And I hope you are clearly noticing they are not same. Because 3 to the power 30 and 3 to the power 15,625 is totally different. Yes or no? Did you all get this? So that's the whole point I'm trying to give you. This is n minus 1 to the power m. This is not whole raised to the power m. Getting it, everyone? That's great. So with this, shall I move ahead from here? I repeat, this is one of those most crucial properties on which JEE Mains will definitely ask you a question. In every single shift, there will be a question on it. Trust me, mark my words. Let me begin this discussion with this question. So here we are with another question for the day. Let's take a 10 minutes break. We'll resume with 10 minutes. 12:30 it is. 12:40 will resume. And I'll be really happy if you could also take a break, stretch yourself, walk a little, hydrate yourself, and then come back. So 12:40 will resume. Is that okay? Hello. Students, just give me a quick response. Am I clearly audible? I hope you can hear my voice. Okay, so there we are with our discussion. Continuing further. Everyone, can you all hear me? Can you all see me? Shall we resume with our discussion? So this question, what does it say? We'll solve it. So let's quickly conduct a poll as well, so that we can understand how many of you are getting comfortable with this concept now. So shall we? Let's quickly start with the poll. I'm sure it's already late. Not most of you are watching, but still, let's be hopeful and let's see how many of you participate. So I'm told A is a 3 by 3 matrix. Determinant of A is said to be 2. And then you're asked the value of this expression. If I could simply use the basic idea here. Great. So with this, what I'll be doing here is a simplest thing here. The basic thing here. That, sir, forget this whole question. Let us simplify this step by step. So if I could simplify this step by step, this 3 can I take out? I hope one property which we have learnt already was this one. I'll do it in 2 parts, in 2 pages technically. At 1 page, I'll write all the formulae, and at 1 page, I'll write the solution. So I hope you remember this property. K times determinant of A is always given by K to the power n times determinant of A. So this 3 here is behaving as that K. So K times adjoint of something. So I hope you are remembering and understanding this, that adjoint of a matrix, that matrix was A. So that was 3 by 3. So adjoint of something will be a 3 by 3 matrix. And that matrix getting multiplied by a scalar. Yes or no? Great, excellent. With this, I'm glad. With this 3 when comes out, it will come with power 3, K to the power n. So here when it comes out, I hope you're realizing this 3 when comes out, it will come out with 3 to the power 3 times determinant of adjoint of determinant of 3a times a square. I hope you're getting it comfortable. Although, how do we deal with this part? Let's talk about that as well. Don't worry. But one thing I want to clarify here, that how did I take this 3 out? Did you get that? Everybody. Now, one more thing I want to discuss with you is that can we simplify this part? Although you could have simplified it outside in, but let me do this part as well, some simplification, so that this part also stays sorted. Here, I'll simplify this part 3 times determinant of A. So if I am interested in simplifying 3 times determinant of A, this part I'm simplifying here. Again, what is it going to be? Is it again not going to be 3 as a scalar coming out as power n, which is 3 times determinant of A? So what is determinant of A? That's 2. So this is going to be 3 cube into 2. Can I write it like this? Although you know the value here, but I'll write it like this only. I'm really sorry. This is 3 cube, right? Because this is given in powers of 3 only. So yes or no? So I'll write it as 3 cube into 2 to the power 1. So there, if I simplify it here, 3 cube into 2 to the power 1. So there, this particular part is given as 3 cube already outside, determinant of adjoint of this thing here, which is determinant of 3a. So that I'll write as, what did I get it as? 3 cube into 2 to the power 1 times determinant a. Was it a square? Yes, it's a square. And then this gets closed like this. Everyone with me so far without any confusion? Yes or no? Or shall I repeat that? Yes or no? All the participants. What did I just do? I'm keeping this 3 cube outside just like that. Determinant stays like that. Adjoint stays like that. Nothing happens. This 3a determinant. So 3 comes out as 3 cube into determinant of a. Determinant of a is 2. So it is simply written like this. Now I'll take you back to those properties which we have discussed, and one of those most important properties which I told you that it will be asked almost every year in almost every single shift by JEE. Where is that property here? Now, look at this particular property. Do you remember it? Adjoint of adjoint of adjoint a lot many times. Rather, let's say m times. Its determinant is determinant a to the power n minus 1 to the power m. If I could use this property here, I think almost 80 to 90% of our question is done. Why and how? Let's talk about that here. Forget that whole thing. I am saying that I am simply relaxing it to this, that 3 coming out as 3 cube times, I'm getting this as adjoint of, this is something constant. Let's write it as, of course, 3 cube into 2 to the power 1 times A square. So that's a matrix. Yes or no? So adjoint of something scalar into a matrix, let's treat it as a matrix, and its determinant. Do you remember that property? I hope you do. That property says what? Sir, this 3 cube staying outside, this 3 cube staying outside like that. Now, determinant of A. But this is the matrix. The whole matrix is 3 cube into 2 into A square. So this is 3 cube into 2 into A square. Yes or no? This whole thing, I hope you're understanding this whole thing, determinant of this whole thing raised to the power n minus 1. What is n minus 1 here in this case? What is n minus 1 here in this case? I hope you're noticing n minus 1. Sir, n minus 1. N is the order. So n minus 1 will be 3 minus 1. And that is raised to the power m. M is the number of times adjoint is appearing. So adjoint is appearing only once. So this will be raised to the power 1. That doesn't matter. Do I really need to write it? So I'll stop here. Everyone comfortably got it. I repeat, the whole logic which I have used here is that determinant of adjoint of A. This property I have used, which is determinant of A to the power n minus 1 first of all, raised to the power m. M represents number of times adjoint is appearing. It is appearing only once. So it will be restricted to this only. That's exactly what I have done here. Here in this case, this whole is your matrix. Its adjoint's determinant is needed to be taken. So it will be determinant of this matrix raised to the power n minus 1. Able to process all what I've said so far comfortably, all the participants, or shall I re-explain that? Yes or no? Any confusion related to this so far? Now what I'll do is, I'll simply write this as 3 cube, which stays untouched. Nothing much is needed to be done. Times determinant of 3 cube into 2. I'll write this also like that only. Into matrix A raised to the power 3 minus 1. That's 2. Comfortably getting it, everyone? Yes or no? Now what I'll do next is the simplest task, which says that here, if 3 cube into 2 is taken out, again I'll use this property. Which property? This one. That here, determinant of k is k to the power n times determinant of a. So if I use that property again, I'm keeping it very simple, very slow, so that you are able to understand and process everything. So this 3 cube stays outside. This ka, so this k when comes out, this is 3 cube into 2 to the power n. N is 3. But this whole will be raised to this power 2 as well. Yes or no? Getting it, everyone? Or shall I repeat it? I repeat, 3 cube stays like that. This is k, comes out as k to the power n, but it already has this power 2, so this power 2 should also be raised. Yes or no? And there I'm left with determinant of a. There I'm left with determinant of a. K to the power n, determinant of a. But don't forget that this is raised to power 2 as well. I think I'm very close to getting my answer finally, because I think we'll be just simplifying all the terms and we'll be getting the answer. So this is 3 cube. This is 3 cube to the power 3 into 2, that's 6. So this whole thing can be written as 3 cube into 2 to the power 1 whole raised to the power 6 into determinant of a, that's 2. So this is 2 square. So it's simply a matter of simplifying this. And once you simplify this, you will get the final answer, which you all are pretty good at doing. But if you are still confused, let me do it. This is 3 cube, this is 3 to the power 6. I am given 6 to the power something, right? I am given 6 to the power something. So I need to club the powers of 2, which I'll do later. Don't worry. 3 cube, 3 cube. This is 3 to the power 18. So this is 3 cube into 3 to the power 18 outside. 6 into 3, that's 18. This is 2 to the power 6. This is 2 to the power 6 into 2 to the power 2. So this leaves you with 3 cube and 3 to the power 18. I'm not, merging right now. 2 to the power 8 it will be, because powers are added. So if I snatch 3 to the power 8 from here. So this will be 3 cube into 3 to the power 10 into 3 to the power 8 into 2 to the power 8. Sir, why are you doing it? Because I'm seeing 6. Am I making any mistake? Because I see a problem here. Because 2 to the power 8 we have. So is there any problem? Did I make any mistake? I don't think so. I absolutely don't think so. Because I'll be receiving it as 3 to the power 13 into 6 to the power 8. So I think there is something wrong with the typing here, because I doubt. Let me cross check it one more time, right? If you are watching it sincerely, you also tell me, where did I commit any error or mistake? Did I miss anything? Let me go step by step. What did we do? I think 3 cube came out. Adjoint of determinant of 3a square it was. Then this came as 3 cube into a, which is 2. So this is 3 cube into 2a square. Then it remained as 3 cube into 2a square whole raised to the power 3 minus 1. That's 2. So we are going great. So 3 cube into 2. Okay, I made a mistake. This was already a square. I hope you're realizing it. I forgot taking it as a square. I think I mistakenly wrote it as a. That's where the mistake was committed. I corrected. I'm correcting it. Hold on for a while. This is not a. When I switched between the pages, I mistakenly wrote a square as a. I don't know why and how, but I think I made a mistake. Let me correct it. So I forgot noticing it. I repeat, one mistake I have committed was that it was a square here. I don't know why and how. I think I wrote a 2 here, so I might have mistakenly written as a. So with this simple silly error which I have committed, shuffling between the pages when I did, this a square mistakenly I wrote as a, and that whole thing went wrong. Yes or no? So if I correct it, I think other things are correct. 3 cube is there, 3 cube is there, 2 is there, a square is there, and so I think the job is done. Now what I'll do is simply do this. 3 cube stays like that. Now this is Ka. So Ka's determinant, when you do, it comes out as k to the power n. So this will be 3 cube into 2 whole raised to the power n, which is 3. But this n is raised to the power this 2 as well. So this is 2 times determinant of a square whole square. I hope no confusion so far. Everybody getting it? Or shall I repeat it? I repeat. 3 square into 2 is k, scalar. That comes out as power n, k to the power n. But there is a power 2 already, so that 2 also comes out. And then you're left with a square's determinant, and this square is already there. So it's simply a matter of simplifying this now. Let's quickly do it. 3 cube stays like that into 3 to the power 3. I hope you're paying attention. So 3 into 2 is 6. So I'll write it like this only. That 3 cube into 2 whole raised to the power 6. This is determinant a to the power 2 into 2. That's 4. Right? And determinant a is 2. So can I replace it as 2 to the power 4? Everyone comfortably getting it? Yes or no? So I probably will get the answer at this stage now, because I think this will give me what? 3 cube. 6 into 3. I hope your understanding is 3 to the power 18. This is 2 to the power 6. And this is 2 to the power 4. So I'll get 2 to the power 10 from here. Yes or no, all the participants? So I'll get 2 to the power 10 from here. So if I want to make a 6, so 2 to the power 10 will be clubbed with a 3 to the power 10 here. But if 3 to the power 10 is snatched from 3 to the power 18, it is 3 to the power 8. So this is 3 cube into 3 to the power 8. It is still balanced, just like what we have received, but I'm trying to frame it like what we are given in the option. So I think this is 3 to the power 8 plus 3, that's 11. This is 3 into 2, that's 6 to the power 10. 3 to the power 11, 10 to the power 6. Sorry, 6 to the power 10. So that's your option D, 3 to the power 11, 6 to the power 10, right? That's your option D. I'm sure some of you must have tried doing it and gotten the answer. Nobody? It's perfectly fine. Great. But I hope everybody understood this explanation. Everybody got the whole idea, or any part of this question which you need, which you want to be explained. Everybody got the whole question, yes or no? Can I move ahead from here? Now with this, let us try another question, shall we? What does this question say? It says, you're given a matrix A, okay. You're given a matrix B, okay. You're given a matrix C, okay. And then you're asked this, okay. Shall we go one by one? Shall we go one step by one? So I'll begin with this, adjoint of B upon determinant of C, okay. What is adjoint of B? I think adjoint of B. B is adjoint of A. So in the numerator, if it is adjoint of B, it is adjoint of B. B is adjoint of A, so it is adjoint of A. Yes or no? In the numerator, this is what we have. I repeat, adjoint of B. So adjoint of B. But what is B? B is adjoint of A, so adjoint of A. Wholly divided by determinant of C. What is C? C is 3A. So it is 3 times determinant of A. Comfortably getting it? And for this, do you not know the properties we have discussed already, haven't we? So the properties, if I could use, will say, set determinant of adjoint of A is determinant of A to the power n minus 1. A is a 3 by 3 matrix. So 3 minus 1, that's 2. Raised to the power, number of times adjoint is appearing 2 times. So it is 2. Remember that property? Yes or no? We have just discussed it. Determinant of adjoint of A is determinant of A to the power n minus 1, order minus 1, 3 minus 1 is 2. Whole raised to the power, number of times adjoint is appearing, that's 2. Divided by 3. 3 is 3, but as a scalar, if it comes out, 3 to the power n times determinant of A. Getting it, everyone? Determinant of Ka is k to the power n determinant of A. But with this is a to the power 2 square. 2 square is 4. So it is determinant of A to the power 4 divided by 3 cube into determinant of A. So that is determinant of A cube divided by 3 cube. Now my whole point boils down to finding determinant of A. If I could crack determinant of A, my job will be done. So let's try and work on finding determinant of A. Everybody understanding whatever is being done? Understanding or not? Yes or no, students? So determinant of A, if I want to find, shall I teach you something really interesting? Sarah's rule, shall we do that? Although we have done it previously as well in the chapter determinants, but if you have missed it, let's quickly learn it here. Sarah's rule says that this is 1, 1, 2. Shall I do it here only if you are okay with that? Sarah's rule says repeat the first 2 rows. So 1, 1, 2 you write here. Then 1, 3, 4 you write here. Then what does Sarah's rule say? Pay attention everyone, it's very interesting rule. Sarah's rule here says that now, go ahead with this. Multiply 1, 3, 3, that's 9, write it here. Multiply 1 minus 1 into, that's minus 2, write it here. Multiply 1, 1, 4, that's 4, right here. Add them up and from this subtract. Product of 2, 3, 1, that's 6. Product of 4 minus 1, 1, that's minus 4. Product of 3, 1, 1, that's 3. With this, what do we get? Sir, 9 plus 2, that's 11, I think. Yes or no? Yes or no? And this is 6 minus 4, that's 2 plus 3, that's 5. And 11 minus 5 is 6. So that we receive as 6. Determinant of A we have received as 6. And if we have received determinant of A as 6, this here in the numerator is 6 cube divided by 3 cube. 6 cube is what? 2 into 3 whole cube. So 3 cube are cancelled. I'm left with 2 cube. That leaves you with 8 as the answer. Option A must have been marked by. Let's see how many of you got it right. Although I forgot starting a poll. But I'm sure some of you must have gotten 8 is the answer. Everybody understanding it, everybody going through it, everybody understanding it, yes or no? Everybody, yes or no? Shall I move ahead from here? Shall we try one more question? It says number of symmetric matrices. They're asking you number of symmetric matrices, okay, of order 3 with all the entries from this set 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the 10 digits. I'll be really happy if some of you could tell me the answer in the chat box. So let's quickly start a poll. Let's see. So here I need to form a 3 by 3 matrix. Okay. So 3 by 3 means what? Sir, 3 by 3 means 1, 2, 3, 4, 5, 6, 7, 8, 9. They are telling you that how many symmetric matrices can you frame which has entries as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I hope in the beginning of this session only, I made you do a question where we did something really interesting. Do you remember that 12 by 12 question? A matrix of order 12 by 12. Remember that? That same logic, if I could apply here, my job will be done. If you remember that, sir, you can do anything with these principal diagonal elements. They can be anything. They don't matter at all. They can be anything. Now the job boils down to the simple fact, what you do with the upper triangle or the lower triangle. Remember that? Yes or no? Yes or no, everyone? So sir, it is totally your choice. Let's say you're playing with the upper triangle. So what you're doing is you're fixing the principal diagonal elements and you're fixing these elements, upper triangle elements. So once you have fixed them, I hope you are clearly noticing that, sir, this will be dependent on this because it is symmetrical. This element will be dependent on this because it is symmetrical. And this element here will be dependent on this. So you still have the liberty to choose these six elements independently, 1, 2, 3, 4, 5, and 6. Now, if I apply permutation and combination, what does this say? The logic of permutation and combination says that if I use basic principle of counting, I approach this element and ask it, in how many ways can I fill your place? So it will say you can fill me by either 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9. So this position here can be filled in 10 ways. 10 ways. So this place here can be filled in 10 ways and means multiplication. This place, if I ask, in how many ways can you be filled? It will again say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ways. So this place again can be filled in 10 ways and this place can be filled in 10 ways and this place can be filled in 10 ways and this place can be filled in 10 ways and this place can be filled in 10 ways. So technically, I have 10 to the power 6 ways to fill these 6 places by 10 digits or numbers. And those possibilities will have these 3 possibilities replicated by them, because whatever comes here, let's say 3 comes here, so 3 will come here. Let's say 4 comes here, so 4 will come here. So these cases are dependent on them. So they'll automatically get adjusted because we want to ensure that it is symmetric. So are you not realizing there are total 10 to the power 6 ways of creating symmetric matrices based on these 10 elements of order 3? How many of you understood it? How many of you got the logic? How many of you were able to crack it? How many of you were able to think like this? And if you have any other approach, do tell me in the comments. I'll really appreciate your approach or idea. Everybody getting that? Everybody understood the whole idea? Let's see how many of you got it right. So the answer was option B. And I'm hoping somebody sincere must have applied or responded. No worries. Let's look at the next question. Here comes the concept of inverse, which we are going to deal with matrix polynomial. So matrices can be represented in terms of equations, and they are called characteristic equations, matrix polynomial, although there is a lot more which we have covered in our paid batches. But right now, I'll just give you the simple glimpse that here, if I'm asked to find out the inverse of A, how will I do it? I'll say to find the inverse through a matrix polynomial, through a characteristic equation, what I'll do is A square minus I, I'll shift there. So I'll receive as A minus A square. They are asking you to find the inverse. So inverse of A exists. If inverse of A exists, which means A is invertible, that means A is non-singular, that means determinant of A is not 0. So I can pre-multiply or post-multiply both these sides by A inverse. So when I do so, what do I get? If I am multiplying it by A inverse, so A inverse into I is A inverse. This is A inverse into A. This is A inverse into A square. If you want, you can write A square as A into A. Now that's the beauty here, that I hope you're realizing this is A inverse on the left, A inverse into A, that's identity matrix, A inverse into A, that's identity matrix into A. An identity matrix into a matrix is that original matrix, and that's how you define A inverse as I minus A, which is given in option D. So I repeat, whenever you're given matrix polynomial, the characteristic equation of a matrix, by that also you can find out the inverse of a matrix. Did you all get that? Although there is a lot in it, which I'll explain there. So I think I forgot starting a poll, but I hope you got it. How did we get option D? Everybody understood that? Or shall I repeat it? All the participants, yes or no? With this, let us move towards the next thing here. System of equations. This is exactly what we have discussed when we talked about determinants. I think I have given you a complete clarity on this system of equations being consistent, having solutions, no solutions, infinite solutions. Everything we have covered in detail when we talked about determinants. That same replication is being done here. But if I'm asked to solve this system of equations by using matrix method, how do we do it? Let's learn it. And with this method, you'll get complete clarity on that whole concept one more time, shall we? So let's talk about everything step by step. Solve the following system of equations using the matrix method, which has first equation as 1, 2, 1, 7, 1, 0, 3, 11, 2, minus 3, 0, 1. Did you understand my language, whatever I've said so far? I am saying that here, if I want to write the coefficients of xyz, which I denote by, let's say, A. So matrix A here will be given by coefficient of xyz in the first equation are 1, 2, 1. Coefficient of xyz in the second equation are 1, 0, 3. Coefficient of xyz in the third equation are 2, minus 3, and 0. This is your matrix A. Similarly, I'll define a matrix X. So matrix X is your variable matrix, which is a column matrix given by x, y, z. And similarly, you define a matrix, let's say B. That is your constant matrix given by a column matrix of these constants 7, 11, and 1. This contains 7, 11, and 1. So I hope by matrix multiplication, you would all agree that AX is equal to B will create three equations, because when 1 to 1 multiplied with XYZ will give me 7. When 103 multiplied with XYZ will give me 11, the second equation. And the third row 2 minus 3, 0, when multiplied with XYZ will give me 1, which is your third equation. So AX is equal to B is your system of equations here. Getting it, everyone? Comfortably understanding it, yes or no? With this, I hope you all must agree that, sir, if you multiply A inverse from left hand side on both the sides of this equation, you will say that A inverse into A into X is equal to A inverse into B. A inverse into A is identity matrix into X is equal to A inverse B. So if I really wish to define X, it will be given by A inverse into B. What is A inverse? A inverse is adjoint of A upon determinant of A into B. So that's what I need to find. I need to find three things. I need to find adjoint of A. Then I'll have B, which I have already written. Then adjoint of A, I'll multiply with B. Then I'll find determinant of A. And then adjoint of A into B, that product I'll divide by determinant of A. And once I've done it, I'll have X, Y, Z at my fingertips. In boards, if you're asked this question like this is how it's supposed to do. In JEE, if you're asked a question like this, of course you will not be, but if you are asked something like this, you will be solving these three linear equations with three variables, either by substitution or elimination, and you'll get the final answer. You know both the approaches. But let's say in the boards, I'm doing it. So how will I do it? I'll first of all find adjoint of A. So how will I find adjoint of A? Let's work on that. So I'm working on finding adjoint of A first, because I need adjoint of A. So this is our matrix A. You know how to find its adjoint, yes or no? Sir, to find its adjoint, first of all, let me quickly write its minor. So minor, and then I'll write cofactor directly. I hope you're okay with that. So if I start writing its minor, first of all, for 1, I hope I can do it directly. 0 plus 3. Sorry, plus 9. So that's 9. Getting it, everyone? I repeat, 0 plus 9. So that's 9. For 2, it will be 0 minus 6. Yes or no? For 1, it will be minus 3. 0. Yes or no? For 1, pay attention, everyone. 0 plus 3. For 0, it will be 0 minus 2. I hope you're noticing it. For 3, it will be minus 3 minus 4, which is minus 7. For 2, it will be 6 minus 0. For minus 3, it will be 3 minus 1. That's 2. For 0, it will be 0 minus 2. So that's how I wrote minors. You're comfortable with this process, yes or no, all the participants? Now, once I've written the minors, what I'll do is I'll write cofactors. So for cofactors, what I'll say? Plus, minus, plus, minus, plus, minus, plus, minus, plus. That's the cofactor of A, yes or no? Now, if I take its transpose, I'll have the adjoint, yes or no? So I'll just take its transpose very quickly and I'll write the adjoint. So adjoint of A, I am in a position to write now. Its transpose will be adjoint of A. So 9, 6, minus 3 will be my first column. Minus 3, minus 2, 7 will be our second column. Minus 3, minus 2, and 7. And 6, minus 2, minus 2 will be our third column. 6, minus 2, minus 2. So that's how you have found adjoint of A. Comfortable, everyone? One more thing I'll require here at this stage is to find determinant of A. And I think you, without even expanding, you can do it, because if I choose any row, and multiply that row with its corresponding cofactors, I think I'll have the value of the determinant of that matrix, the simplest property which we have learned so far. So will I not say that, sir, here determinant of A will be given by this 1 multiplied with its cofactor, which is minus 3, plus this 0 into minus 2 is 0, plus this 3 into 7, that's 21, and 21 minus 3, I hope is clearly plus 18. I hope it's visible here. Getting it or not? So we have adjoint of A, we have determinant of A, and we have the matrix P. And if we have all these things, I think our job is absolutely done. Why am I saying this? Let's talk about that now. I hope so far there is no confusion on whatever is done. Because now, if I could write my final expression, what was that expression? Do you remember that? The question was what? To find x. X is adjoint of A into B by determinant of A. So if I am really interested in x, which is adjoint of A times B divided by determinant of A. What is determinant of A? That was 18. So I'll have 1 by 18 as a scalar outside. Now what is adjoint of A? This is this. So I'm rewriting it just to ensure that we have some space. This is 6 minus 2, and this is minus 3, 7 minus 2, whole multiplied by B. What was B? Do we have B somewhere? I think B was 7, 11, 1, right? Constants. So it is 7, 11, and 1. That's your B. So if you do it, you will finally find X, Y, Z respectively. Right. I hope matrix multiplication you all are comfortable with. So I'll choose rows from here and columns from here. Right, students? So here if I do it, first of all, I hope no confusion regarding this. That, sir, you are going to be left with 1 by 18 outside. So I'm keeping this outside, multiplied with, pay attention everyone, 9 into 7, 63, minus 11 into 3, minus 33, plus 1 into 6, that's plus 6. That's your first element. Then this row I'll choose with the same column again. So what will I have? 6 into 7, 42. Then 11 into 2, minus 22. Then 1 into minus 2, that's minus 2. Then I'll choose this third row with this column. So what will I have? Minus 3 into 7, minus 21. I'm really sorry. Minus 21. Then 11 into 7, that's plus 77. Then 1 into 2, that's minus 2. So what you now need to do is simply calculate it. Once you have done that calculation, your job will be done and your question will be there right there in front of you. So 1 by 18 is outside and this whole is equal to x. What was x? X was your variable matrix, x, y, and z, the values of x, y, z. So this gives you what? 63 minus 33, that's 30. 30 plus 6 is 36. So this is 36 here. This is 42 minus 22. That I think is 20. Minus 2 is 18. Yes or no? And this here leaves you with what? This here leaves you with 77 and 23. So this is 23, right? So this leaves you with what? 54, correct me if I'm wrong, plus 54, right? So that is 54. So with this, if I push this 18 inside, so 36 by 18, that's 2. 18 by 18, that's 1. And 54 by 3 is, 54 by 18 is 3. Yes or no? So I think by comparison here, will I not finally come to this conclusion that x is 2, y is 1, and z is 3? So the triplet which satisfies these values are going to be 2, 1, and 3. Did you understand this whole method of matrix? Yes or no? Everybody got it? Everybody understood it? Everybody, yes or no? So far, in the previous session, we have done determinants. In today's session, we have covered matrices. I am simply telling you a simple fact that in determinants, if you simply know one thing, expansion, second thing, its properties, third thing, Kramer's rule, and fourth thing, the properties. Same got extended here with matrices, its types, right? It's different types, and then adjoint and inverse and transpose based properties and rules and formula. If you know it, trust me, this combination will give you minimum 2 to 3 questions in JEE mains. That means 12 marks if done accurately. And most of you who have started seeing that in JEE mains, that 12 marks from mathematics section is something not anybody can do. So those who are very much in love with asking the question that, sir, give us the most important chapters. So if somebody claims vectors in 3D are the most important chapters, I'll claim determinants and matrices is also one of those important units from where you can fetch 12 marks. And it is something really huge, something really worthy. one chapter technically. Matrices and determinants are interdependent. So one unit technically gives you 12 marks in JEE mains. Can you believe that? All I'm asking you to do is that, of course, this one shot, which we covered previously determinants, and now we have covered matrices. To understand concepts, to understand theory with apt examples and questions, it is sufficient to understand the theory completely, thoroughly, wholly. But I'll still suggest you one thing, that now to consolidate it, to get a good command over it, to develop a good understanding over it, you need two things, PYQs. First of all, 2020 onwards, all the PYQs of JEE mains, do them all. And then advanced PYQs from 2000 onwards. So last 26 years PYQs you do. From 2000 onwards, 2026, all these PYQs. And when you are solving these PYQs, mind you students, categorize your questions as easy, moderate and hard. The questions which you are finding easy, just do them and move away. Moderate ones which you found a little difficult, but after seeing the solution, you were able to solve them. So those you keep for your revision, you will see them. But harder ones which you couldn't do, which you find hard, those are the concepts which you are weak at. So keep them strictly for your revision, and when you revise them someday in future, solve those questions again. Keep them marked like this. And these are your questions where you need your understanding better. So that should be your ideal strategy for the upcoming days. So I hope I have tried giving you the whole idea, the whole philosophy, the whole understanding. With this session ends here on matrices and determinants. Technically, determinants got covered previously in the last one shot. This was the one shot on matrices, and I'm sure you must have learned a lot of things. Tried covering all the theory, concepts, formulae, applications with apt examples and relevant questions of JEE mains. But yes, I totally accept that this is not sufficient. You need more practice. More practice can be done by solving as many previous year's questions as you can, which we are already doing in our paid batches. Laksh for class 12th JEE aspirants, Arjuna for class 11th JEE aspirants in pure English. If you want to be a part of it, you can. The links are given in the description. And one most important, crucial thing, the entire PDF. That means all the notes of this entire chapter matrices, which got covered in this one shot. If you want to avail, if you want to have them, you can have them by following our WhatsApp channel. Right after this channel, right after this session, the entire PDF will be uploaded there. Sir, how do we follow your WhatsApp channel? You can check the link given in the description. From there, you can get to our WhatsApp channel, and there it will get uploaded right after this session. The entire PDF of this entire chapter matrices, which just got covered, so that you can revise it, so that you can study it, so that you can still go through all the notes with this one single PDF. I think this is all what we can do right now. Thank you so much, students. You have been a really great audience, cooperating sincerely and watching this. We really loved it. Thank you so much. Thank you so much. It was really nice being with you all. Good night, everyone. Take a good care of yourself. Good night.